Why does anything exist instead of nothing? There is a question sitting underneath every single thing you have ever known. It is hiding behind your morning coffee, behind the chair you are sitting in right now, behind the device you are using to watch this. The question is simple to say, but almost impossible to answer. Why is there something instead of nothing? Not why is there life, not why is there a universe with stars and oceans, and people who fall in love and start wars. Just why is there anything at all? Why did existence even bother to begin? Think about that for a second. Nothing means nothing. No matter, no energy, no space, no time, no laws of physics, not even empty darkness, because darkness is still something. True nothing would be the complete absence of absolutely everything, including the rules that might allow something to start. And yet here we are. Atoms exist. Stars exist. You exist, reading or listening to these exact words. Somehow, against what should have been the simplest and most stable state possible, which is nothing, we ended up with something instead. Here is where it gets uncomfortable. Most people assume science has this figured out. They think somewhere in a physics textbook there is a clean equation that explains why existence kicked off. There is not. Even the Big Bang, the event we point to as the beginning of our universe, does not actually answer the question. The Big Bang explains how our universe expanded from an extremely dense and hot state into what we see today. But it does not explain why there was anything there to expand in the first place. Asking what caused the Big Bang is like asking what was happening 1 second before time itself began. The question almost breaks the language we use to ask it. Physicists have tried. Some suggest that empty space is not truly empty, that what we call a vacuum is actually buzzing with quantum fluctuations, tiny bursts of energy popping in and out of existence due to the uncertainty built into reality at the smallest scales. It sounds like a clever workaround, like maybe nothing is unstable and something has to eventually leak out of it. But here is the catch that most people never hear. For quantum fluctuations to happen at all, you still need the laws of quantum mechanics to already exist. You need space for the fluctuation to fluctuate in. You need some kind of underlying framework. So you have not actually explained why there is something instead of nothing. You have just pushed the mystery 1 step further back and renamed it. This is the part where most explanations quietly fall apart, and almost nobody points it out directly. Every scientific model that tries to explain existence starts by assuming some kind of structure is already there, some kind of potential, some kind of law. But where did that come from? If nothing truly means nothing, there should not even be the possibility of quantum rules, or potential energy, or mathematical structure. The deepest version of this question is not really a science question anymore. It bleeds into philosophy, because you are essentially asking why existence is even a coherent option in the first place. And this is exactly why so many brilliant minds across history have circled this question and walked away without a real answer. Gottfried Leibniz, one of the most important philosophers in history, asked almost this exact question centuries ago. He wondered why there is something rather than nothing, since nothing seems so much simpler and easier than something. Stephen Hawking, one of the most respected physicists to ever live, openly admitted that even with everything we know about cosmology, the question of why the universe bothers to exist remains unanswered. When people at that level, people who spent their entire lives studying reality at its deepest layers, admit they do not have the answer, that should tell you something. This is not a question you missed in school. This is a question humanity has not actually solved. If you have ever lain awake at night with your mind quietly spiraling into this exact thought, wondering why there is anything here at all, why you are conscious instead of simply not existing, you are not overthinking. You are not broken. You are doing exactly what your brain was built to do, which is search for explanations. Humans are pattern-seeking creatures. We are wired to ask why behind every effect we see, because that wiring kept our ancestors alive, helping them predict danger and find food and understand cause and effect in their environment. So when that same wiring turns inward and points at existence itself, it makes complete sense that the question feels heavier than almost anything else you could think about. You are using a survival tool built for small, daily problems and pointing it at the biggest mystery there is. So if science cannot fully explain it, and philosophy cannot fully explain it, where does that leave us? It leaves us with a quiet possibility that is honestly kind of unsettling once you sit with it. What if the universe does not actually need a reason to exist? What if asking why something exists instead of nothing is built on an assumption that nothing was ever even a real possibility to begin with? That single idea, if true, would not just answer one tricky physics question. It would completely change the way you think about your own existence, your consciousness, and whether anything you call reality is even built the way you assume it is. Is consciousness fundamental to reality? You are reading these words right now. Something inside you is taking these letters and turning them into meaning, into thought, into an actual experience of understanding. That feeling of being aware, the sense that there is someone home behind your eyes, has a name in science and philosophy. It is called consciousness, and here is the part that should genuinely unsettle you. After centuries of studying the brain, after mapping nearly every region and every neuron pathway we can access, we still cannot explain how consciousness actually happens. Not really. Not in the way we can explain digestion or how the heart pumps blood. Most people assume this is settled. They assume scientists know that consciousness is just something the brain produces, like sweat from skin or sound from a speaker. But that assumption hides one of the strangest unsolved problems in all of science. Philosopher David Chalmers gave it a name that stuck, calling it the hard problem of consciousness. The easy problems, relatively speaking, are things like explaining how the brain processes light into vision or how it stores memories. Difficult, but doable, because they are mechanical. The hard problem is different. It asks why any of that processing comes with an actual felt experience at all. Why does seeing red feel like something, rather than just being a quiet electrical signal happening in the dark with nobody experiencing it? Here is where it gets uncomfortable. Imagine you built a machine that could detect red light and respond to it perfectly, sounding an alarm, changing its behavior, doing everything a human does when they see red. You could build that today, but would that machine actually experience redness the way you do? Would there be a felt quality to it, an inner sense of color? Or would it simply be matter moving in a more complicated pattern with nothing behind it? Nobody can answer that with certainty, not for machines, and honestly, not even fully for other humans. You assume other people are conscious because they act like you and tell you they feel things, but you cannot directly access their experience. You are essentially trusting that consciousness is there, the same way you trust gravity will work tomorrow without ever truly seeing the force itself. This is where the question turns from strange to almost reality-breaking. Some scientists and philosophers have started seriously entertaining the idea that consciousness is not something the brain creates, but something fundamental to the universe itself, similar to space, time, or energy. This idea is sometimes called panpsychism. It does not claim that rocks are sitting there thinking complex thoughts. It suggests that some extremely basic form of experience might exist at the smallest levels of reality, and that when matter organizes itself into something as complex as a brain, that simple raw experience combines into the rich conscious awareness you have right now. It sounds bizarre at first, almost like science fiction, but it became a serious topic precisely because the alternative explanation, that consciousness simply appears out of nowhere once matter becomes complex enough, has never actually been proven either. Nobody has shown the exact point where unconscious atoms become a conscious experience. There is no equation for it. There is no line on a chart where awareness flips on. This is not just some abstract academic puzzle floating in philosophy departments. It directly affects how we think about your life, right now, in this moment. If consciousness is something the brain produces, then you are essentially a biological machine running incredibly advanced software. And when the machine stops, the experience simply ends, like a screen turning off. But if consciousness is fundamental to reality itself, something the universe is built from rather than something it merely produces, then your awareness is not just a side effect. It becomes a basic ingredient of existence, as real and as deep as matter and energy. That is not a small difference. That is the difference between feeling like a temporary accident of biology and feeling like you are a genuine expression of something woven into the fabric of reality itself. If you have ever stared at your own hand and had that strange, dizzying moment of wondering how atoms arrange themselves into something that can think and feel and ask questions about itself, you were brushing right up against this exact mystery without fully realizing it. That feeling is not random. Psychologists call this kind of moment depersonalization, adjacent wonder, a brief slip where your normal sense of self loosens just enough for you to notice how strange consciousness actually is. Most people push the feeling away because it feels uncomfortable, almost dizzying, like standing too close to the edge of something enormous. But that discomfort is not a malfunction. It is your mind correctly sensing that it has bumped into one of the biggest unanswered questions in existence. So the truth is this: nobody currently knows for certain whether consciousness is something extra the universe quietly produces once things get complicated enough, or whether it has been there from the very beginning, threaded into the basic structure of reality, waiting for matter to become complex enough to express it. And once you really sit with that uncertainty, you start to realize that the question of who you are and what you actually are is far from settled science. It is one of the open frontiers of human understanding, and you are living inside the mystery right now. Every single time you simply notice that you are aware. Are we living inside a simulation? Right now, as you take in these words, ask yourself something most people never actually sit with for more than a few seconds. How would you know if everything around you, the screen, the room, your own hands, was not physically real at all, but instead something generated, something simulated, something running on a system far beyond anything you could see or touch? Most people laugh this off immediately. It sounds like science fiction, like something out of a movie rather than a real possibility. But here is the uncomfortable truth. Some of the most respected minds in physics and philosophy do not dismiss this idea at all. Some of them think it is more likely than not. This is not a fringe internet theory. Philosopher Nick Bostrom, from the University of Oxford, laid out a formal argument for this back in 2003, and it has been seriously debated in academic circles ever since. His reasoning is almost frustratingly simple once you hear it. Imagine a civilization advanced enough to create incredibly realistic simulations of conscious beings, similar to how we create video games today, just unimaginably more advanced. If even one civilization in the entire history of existence reaches that level of technology and decides to run many simulations, then simulated minds would vastly outnumber real ones. Which means, statistically, if you are a conscious being wondering whether you are simulated or real, the odds actually favor simulated, simply because there would be so many more simulated minds than original ones. Here is where it gets even stranger. This is not just philosophy floating untethered from actual physics. Some physicists have pointed out that reality itself behaves in ways that feel suspiciously similar to a digital system. At the smallest scale, energy does not behave smoothly and continuously the way you would expect from a purely physical reality. It comes in discrete chunks called quanta. Light, for example, does not just flow like a wave indefinitely. It arrives in individual packets called photons. Some researchers have compared this to the way a video game does not render every possible detail of a world continuously. It only renders what needs to be calculated, almost like reality is operating on some kind of underlying code that processes information in pieces rather than as an endless smooth flow. There was even a real moment where this idea bled directly into mainstream public conversation. In 2016, Elon Musk publicly stated that the odds we are living in base reality, meaning the original, true, non-simulated version of existence, are 1 in billions. He pointed to how quickly video games evolved, going from simple pixelated graphics in the 1970s to nearly photorealistic three-dimensional worlds within just a few decades. If technology keeps improving at that pace, he argued, eventually simulations would become indistinguishable from reality itself, and there would be far more simulated worlds created than original ones. Now here is the part that should genuinely make you pause. If you cannot prove with absolute certainty that this is not happening, isn't that incredibly strange to sit with? You cannot stand outside the system and check. You are using your senses, which exist inside the very system in question, to try to determine whether the system is even real. It is like trying to check if a maze has walls by only ever walking through hallways the maze itself created for you. There is no outside vantage point you can access. That alone is one of the more disturbing aspects of this entire question. It is not that the simulation theory is necessarily true. It is that there may be no possible experiment, no test you could ever run from inside the system that would definitively rule it out. If you have ever had a strange moment of déjà vu, or a sudden eerie feeling that something around you felt slightly off, almost staged, you are not broken, and you are not imagining something meaningless. Psychologists explain déjà vu as a small glitch in memory processing, where your brain mistakenly tags a new experience as familiar. But it is worth noticing how often people describe that exact sensation using words like glitch, almost as if some part of the human mind is primed to interpret reality as something that could, in theory, malfunction. That does not prove anything about simulation theory specifically, but it does reveal something important. Human beings are deeply comfortable imagining that the world around them might not be fully stable or fully real. And that openness is not a flaw. It might be your mind correctly sensing how little we actually know about the nature of existence itself. So where does that leave you? It leaves you in a position where some of the smartest people alive cannot rule this idea out, where physics keeps producing strange hints that feel uncomfortably similar to digital behavior, and where you have no way to step outside your own experience to check. Whether or not we are living inside a simulation remains completely unresolved. But simply asking the question seriously, instead of laughing it off, puts you closer to understanding the actual edges of human knowledge than most people will ever get. What happened before the beginning of the universe? Try something for a second. Try to imagine a moment before time existed. Not a long time ago, not billions of years back, but an actual point before there was any before at all. Most people cannot hold that thought for more than a few seconds without their mind sort of slipping off it, like trying to grip water. That difficulty you just felt is not a personal failure. It is your brain running directly into one of the strangest limits in all of physics, because the question of what happened before the beginning of the universe might not even be a question that makes sense the way you think it does. Here is what almost nobody explains clearly enough. The Big Bang is often described, even in documentaries and textbooks, as some kind of explosion that happened at a specific point in an already existing empty space. That description is misleading, and it is exactly why this question feels so confusing. The Big Bang was not an explosion happening inside space. It was the beginning of space itself and the beginning of time itself, all at once, together as a single starting point. According to general relativity, the theory of gravity developed by Albert Einstein, time and space are not separate backgrounds that the universe sits inside. They are woven together into a single thing called space-time, and that space-time had a beginning roughly 13.8 billion years ago. Now sit with the actual weight of that for a moment. If time itself began at that point, then asking what happened before the Big Bang is a little like asking what is north of the North Pole. It sounds like a normal question grammatically, but it is built on an assumption that breaks down the moment you examine it closely. North only makes sense as a direction within a system that has more north available. Once you are standing at the North Pole, there simply is no more north left to go. In the same way, before only makes sense within a system that has time flowing through it. If time itself starts at the Big Bang, there may be no before for the question to even point toward. This is the part that quietly destroys most people's first reaction to this topic. Their instinct is to ask, okay, then what caused the Big Bang? Because every single thing we experience in daily life has a cause that came before it. You drop a glass, it shatters, because gravity pulled it down. Every effect you have ever witnessed had something earlier that triggered it. But causes require time to operate in, because cause and effect is fundamentally about something happening first, and then something else happening after as a result. If there was no before, then the entire concept of causation, the very framework your brain uses to understand literally everything else in life, might simply not apply at the one moment you most desperately want it to. Physicists have not just shrugged and stopped there, though. Some have proposed ideas that try to push past this wall. One theory suggests that our universe is not the only one. and that the Big Bang we experienced might be one bounce in an endless cycle, where a previous universe collapsed and then rebounded into a new expansion, over and over, infinitely. Another idea, coming from quantum cosmology, suggests that asking for a cause before the beginning might be like asking what caused a radioactive atom to decay at the exact moment it did. At the quantum level, some events appear to happen without a specific triggering cause, governed instead by probability rather than a clean chain of causation. If the birth of the universe behaved similarly, then perhaps it did not need a before at all. It might have simply been one of the ways nothing could spontaneously become something. The way unstable quantum systems sometimes shift without anything pushing them. None of these ideas are confirmed. None of them are something scientists agree on with full confidence. And that uncertainty is exactly the point worth sitting with. Stephen Hawking, one of the most respected physicists in modern history, spent years working on exactly this puzzle, eventually proposing a model where time itself becomes smooth and rounded near the beginning, similar to how the surface of the Earth has no actual edge despite being finite. In that kind of model, asking what happened before the beginning is like asking what is south of the South Pole. The question dissolves rather than gets answered. If you feel a strange kind of vertigo trying to picture this, that reaction makes complete sense. Your entire brain evolved inside a universe where everything has a before, where every object, every event, every person has some origin point you can trace backward. You have never once, in your entire life, experienced anything without time flowing underneath it. So when you try to imagine the literal absence of time itself, you are not failing to understand something simple. You are trying to use a mind built entirely out of time-based experience to imagine the one place time-based experience does not apply. That is where this question currently sits. Not solved, not fully understood, but seriously investigated by some of the most capable scientific minds in human history, with multiple competing ideas, no clear winner yet, and a growing suspicion that the answer, whenever it eventually comes, will probably break the rules of how you currently think about cause, time, and beginnings altogether. Does time actually flow, or is it an illusion? Right now you feel like you are moving through time. The moment you just experienced reading those last few words is already gone, sitting behind you in the past, and the next moment has not happened yet. That feels obvious. It feels like the most basic fact of existence there is. Time passes, moment by moment, like a river carrying you forward, whether you want it to or not. But here is something that should genuinely shake you. Many physicists, including some of the most respected minds in the field, do not believe time actually flows at all. They think that feeling, the one you are having right now as you read this, might be one of the biggest illusions the human mind has ever created. This sounds almost insulting at first. Of course time moves, you might think. I just lived through the last 10 seconds, and now they are gone forever. But physics tells a different story, and it starts with Albert Einstein, who showed something deeply unsettling through his theory of relativity. Time does not pass at the same rate for everyone. Someone moving very fast, or sitting near a powerful source of gravity, experiences time differently than someone who is not. This has actually been measured, not just theorized. Astronauts who spend extended time on the International Space Station age very slightly slower than people on Earth, because their speed and orbital position around the planet shift the way time flows for them, even if only by fractions of a second over months. That alone proves time is not some universal clock, ticking the same way everywhere for everyone. It bends, depending on your speed and your position in a gravitational field. But here is where it gets far stranger, and where most people's intuition completely falls apart. If time can stretch and shrink depending on your motion, then the past, present, and future are not as separate as they feel. Einstein himself, in his theory of relativity, described something physicists now call the block universe. In this view, every moment that has ever existed and every moment that ever will exist already exists, all at once, frozen into a single unchanging structure. The same way every page of a book already exists printed in the book, even though you are only reading one page right now. Your sense of moving through time, page by page, might not mean time itself is moving. It might simply mean your consciousness is scanning across an already complete structure, similar to a finger sliding across a page that was already fully written before you started reading it. If that idea is even partly correct, it means something deeply uncomfortable. It means the moment you were born and the moment you will die already exist, sitting there in the structure of reality, just as real and just as fixed as the present moment you are living right now. Nothing is technically passing away or coming into being. It would all simply already be there, complete, and your brain is just experiencing it one frame at a time. The way you experience a movie one frame at a time, even though the entire film already exists on the reel before you press play. So why does it feel like time is flowing then, if physics suggests it might not actually be moving at all? This is where neuroscience steps in, and the explanation is honestly fascinating. Your brain constantly takes in new sensory information and compares it against memory, constantly updating a mental model of what just happened versus what is happening now. That constant comparison creates the felt experience of forward motion, the same way watching individual still photographs flash quickly enough creates the illusion of smooth motion in a film. Nothing is actually moving inside a movie reel. Each frame is just sitting there, completely still, but your brain stitches them together into something that feels like continuous flow. Some physicists now suspect your entire experience of time might work the exact same way, your mind generating the sensation of flow out of a universe that may not actually be flowing at all. This connects to something physicist Julian Barber has spent much of his career exploring, the idea that what we call time might actually just be change, a sequence of different configurations of the universe, rather than time being some separate force pushing everything forward. In his view, there might not be a flowing river of time at all. There might just be countless individual moments, each one complete on its own, with no actual current moving between them, only our memory linking them together afterward into something that feels like a story moving forward. If this idea unsettles you, that reaction is completely understandable, because it touches something deeply personal. If time does not actually flow, then loss does not work the way you have always assumed it does. The people you have lost, the moments you wish you could return to, may not be gone in the way grief tells you they are. They might simply exist at a different point along an already complete structure, a point your consciousness is no longer scanning across, but one that never stopped existing in the first place. Nobody knows for certain which version of reality is correct. Whether time truly flows, carrying the universe forward moment by moment, or whether it sits still as one complete structure, while your mind simply experiences it piece by piece, remains one of the most debated open questions in physics today. And once you really sit with that uncertainty, the simple act of glancing at a clock never feels quite as simple again. Are there hidden dimensions beyond space and time? Hold your hand up in front of your face for a second. You can move it up and down, left and right, forward and back. 3 directions, 3 dimensions, and then time pulling you forward as a 4th. That probably feels like the complete list. That feels like all the room reality could possibly have. But here is something that should genuinely catch you off guard. Some of the most respected physicists alive today suspect that what you just experienced, those 4 dimensions, might only be a small fraction of what actually exists. Some serious scientific models suggest there could be 6, 7, or even more dimensions woven into the fabric of reality. Dimensions you have never seen, never felt, and never been able to point toward, not because they are far away, but because they might be folded up so tightly that they hide directly inside the space around you right now. This is not science fiction borrowed from a movie plot. This idea comes from string theory, one of the most seriously pursued frameworks in modern theoretical physics, an attempt to explain how gravity and quantum mechanics could fit together into one single description of reality. For string theory to mathematically work, for the equations to actually balance without breaking down into nonsense, the universe needs more than the 4 dimensions you experience. Most versions of the theory require 10 or 11 dimensions total. That is not a typo and not an exaggeration. Extra dimensions are not just allowed in this framework, they are required for the math to function at all. So where are they? This is the part that sounds almost impossible to accept at first. The leading explanation is that these extra dimensions are compactified, meaning they are curled up into shapes so unbelievably small that you could never directly perceive them, even in principle, with your senses or with most equipment we currently have. Imagine a garden hose seen from very far away. From a distance it looks like a simple one-dimensional line. But if you got close enough, you would realize the hose actually has a second dimension wrapped around it in a tiny circle, the width of the tube itself. Some physicists believe space might work the same way at an extremely small scale. What feels like empty space to you might actually have additional dimensions curled up so tightly within it that they are completely invisible, hidden in loops smaller than anything we can currently detect, even with our most advanced instruments. Here is where this stops being just an abstract mathematical trick and becomes something that should genuinely unsettle you. If extra dimensions exist, even ones too small to notice directly, they could explain one of the biggest unsolved mysteries in physics, which is why gravity is so incredibly weak compared to the other forces in nature. Electromagnetism is enormously stronger than gravity at small scales, strong enough that a tiny magnet can lift a paperclip against the pull of the entire planet beneath it. Nobody has ever fully explained why gravity is so much weaker in comparison. One theory suggests gravity might not be weak at all. It might simply be leaking out into those extra hidden dimensions, spreading its strength across dimensions we cannot perceive, which would make it appear weaker to us than it actually is within the full structure of reality. This is not just theoretical guessing without any attempt at testing it. Scientists at the Large Hadron Collider, the massive particle accelerator built near Geneva, have actually searched for signs of extra dimensions, looking for specific patterns in particle collisions that would suggest energy escaping into dimensions beyond the ones we can see. So far, no confirmed evidence has shown up, but the fact that some of the most advanced scientific experiments ever built have seriously searched for this tells you something important. This is not a fringe idea floating somewhere outside mainstream science. It is taken seriously enough that billions of dollars in research infrastructure have been pointed directly at trying to find proof. If you are sitting there trying to actually picture a dimension beyond the ones you know, and your mind keeps sort of sliding off the idea, unable to truly visualize it, that struggle is not a personal failure. Human brains evolved entirely within a three-dimensional environment, built specifically to track movement, depth, and distance in exactly three directions, because that was what helped our ancestors survive, judging distances to predators, navigating terrain, throwing objects accurately. Your brain was never built with the hardware to intuitively picture a fourth spatial dimension, let alone a sixth or seventh. Mathematicians can describe these dimensions perfectly well using equations, but equations are not the same as a mental picture, which is exactly why even brilliant physicists often admit they cannot truly visualize higher dimensions either. They can calculate them, they cannot picture them. And that gap between calculation and imagination is part of why this mystery feels so deeply strange. So here is where this leaves us. The universe may contain far more structure than your senses were ever built to detect, dimensions tucked invisibly into the smallest corners of existence, possibly explaining some of the deepest unsolved questions in physics. Nobody has proven it yet. Nobody has fully ruled it out either. And until that changes, the reality you experience every single day, the one that feels so complete and so obviously three-dimensional, might only be the smallest visible piece of something far larger that you are quite literally incapable of seeing. Why does the universe follow mathematical laws? Drop a ball, and it falls at exactly the same rate every single time, anywhere on Earth, described perfectly by an equation discovered hundreds of years ago. Send a spacecraft to orbit a planet millions of miles away, and the same handful of mathematical formulas will tell you precisely where it needs to go, with enough accuracy to land it on a target the size of a parking lot. That should strike you as deeply strange, even though most people never stop to actually feel how strange it is. Why would a physical universe, made of matter and energy and empty space, choose to obey clean mathematical rules at all? Why does reality behave like it is following a script written in numbers? Most people assume this question already has an obvious answer, something like, well, math is just the language humans invented to describe nature, so of course it fits. But that explanation falls apart the moment you look closely at it. Mathematics was not built by watching nature and copying it like a sketch artist drawing a model. Much of mathematics was developed purely inside human imagination, through abstract logic, with no connection to the physical world at all, sometimes centuries before physicists ever needed it. And yet, again and again, those same abstract ideas turned out to describe reality with incredible precision. Here is the example that physicists still find genuinely unsettling. In the 1800s, a mathematician named Bernhard Riemann developed an entire branch of geometry purely as an abstract intellectual exercise, describing curved, multi-dimensional spaces that had nothing to do with physics at the time. It was considered a beautiful but practically useless mathematical curiosity. Then, decades later, Albert Einstein needed exactly that kind of geometry to build his theory of general relativity, the theory that correctly describes gravity, black holes, and the bending of space itself. Riemann was not trying to predict gravity. He was simply exploring pure mathematical structure. And somehow, that structure ended up being the precise language the universe was using all along. This pattern happens so often in physics that one of the most respected scientists of the 20th century, physicist Eugene Wigner, wrote an entire essay about it in 1960, calling it the unreasonable effectiveness of mathematics in the natural sciences. His point was almost embarrassingly simple once you hear it stated directly. There is no logical reason mathematics, something developed largely through abstract human reasoning, should match the actual physical universe so precisely, and yet it does, over and over, in field after field, far beyond what pure chance should allow. This is where the question stops being a fun curiosity and starts becoming something almost dizzying to sit with. If mathematics were just a tool humans built to describe what we already observed, you would expect it to occasionally fail in new situations, requiring constant patchwork fixes. Instead, mathematical equations regularly predict things nobody had even observed yet. Einstein's equations predicted black holes decades before anyone had direct evidence they existed. They predicted gravitational waves, ripples in spacetime itself, almost exactly a century before scientists finally detected them directly in 2015 using incredibly sensitive instruments. The math did not just describe what we already knew. It reached ahead of human observation and quietly told us what we would eventually find, as if the universe had already written the answer key long before we started taking the test. So why would reality behave this way? Some physicists, like Max Tegmark, have proposed an idea so bold it sounds almost like science fiction at first, suggesting that the universe is not simply described by mathematics, but is mathematics. That physical reality at its deepest level is literally a mathematical structure, and our experience of matter and energy is just what that structure feels like from the inside. Under this view, asking why the universe follows mathematical laws is a bit like asking why a circle follows the rules of geometry. The rules are not separate from the circle, layered on top of it. The rules are what a circle actually is. Not everyone accepts this idea, and many physicists consider it too extreme without further proof. But even setting that specific theory aside, the core mystery remains completely unresolved either way. Nobody has ever produced a fully satisfying explanation for why pure abstract reasoning, conducted entirely inside the human mind, keeps perfectly matching the deep structure of physical reality outside that mind. It might be one of the strongest hints we have ever stumbled across that there is something far more fundamental sitting underneath the universe, something deeper than matter, deeper than energy, possibly even deeper than physics itself currently understands. If you have ever felt a strange chill solving an equation that perfectly predicted something real, or felt oddly moved watching a scientific formula match an experiment exactly, that reaction is not irrational. You were brushing up against one of the strangest, unsolved relationships in all of human understanding, the relationship between pure abstract thought and the physical world it somehow keeps perfectly describing, for reasons nobody has ever fully been able to explain. Is free will real, or just a convincing illusion? Right now, you believe you chose to watch this video. You believe you decided, on your own, to keep listening, to keep paying attention, that some part of you sat there weighing options and picked this one freely. That feeling is one of the most basic experiences of being human. You feel like the author of your own choices, the one steering the ship of your own life. But here is something that should genuinely shake that feeling. Some of the most respected neuroscientists in the world have run experiments suggesting that your brain may have already decided your next move before you ever became consciously aware of deciding anything at all. This is not some fringe idea pulled from internet philosophy debates. In 1983, a neuroscientist named Benjamin Libet ran an experiment that quietly shook the entire field. He had participants sit and freely choose, at any moment they wanted, to press a button while he monitored their brain activity. What he found was strange and uncomfortable. Brain activity associated with the decision appeared up to several hundred milliseconds before the person consciously felt like they had decided to press the button. In other words, their brain seemed to start the process of choosing before their conscious mind ever got the memo. The feeling of deciding came after the decision had already quietly begun forming. Later studies, using more advanced brain imaging technology, pushed that gap even further, with some researchers finding signals that could predict a person's choice up to several seconds before they consciously believed they were making it. Sit with that for a second, because most people rush past how strange this actually is. It suggests that the experience of choosing, the feeling of standing at a fork in the road and freely picking a direction, might actually be something closer to a story your brain tells you after the fact, rather than the actual mechanism doing the choosing. Imagine watching a car already rolling forward, then being handed a steering wheel a moment later and told you are the one driving it. You would feel completely in control. You would swear you were steering. But the car was already moving before your hands ever touched the wheel. This connects to something deeper happening throughout your nervous system that most people never think about. Your brain processes an enormous amount of information completely outside conscious awareness, constantly, every single second. By the time something becomes a conscious thought you can actually notice, your brain has already filtered, evaluated, and partially decided on a huge amount of information beneath the surface. Consciousness, according to many neuroscientists, might function less like a captain giving orders and more like a spokesperson standing in front of cameras, announcing decisions that were actually made somewhere else in the building first. But here is where this gets complicated in a way that should make you pause before fully accepting that free will is fake. Critics of this research point out something important. Choosing exactly when to press a button, with no real stakes and no real consequences, is a completely different kind of decision than choosing whether to forgive someone, whether to leave a relationship, or whether to speak up against something you believe is wrong. Some philosophers argue that free will might not mean every single tiny choice is fully conscious from the very first millisecond. It might instead mean something broader, that you, as a whole person built from your memories, values, and reasoning, are the actual source generating these decisions, even if the precise moment of awareness lags slightly behind the underlying brain activity producing it. Under that view, the car was not driving itself without you. You were still the one who built the road, set the destination, and trained the habits that caused the car to start moving in that direction in the first place, even if your conscious mind notices the movement a little after it begins. This debate matters far beyond just being an interesting brain fact, because it touches something deeply personal, something tied directly to how you judge yourself and other people. If free will is mostly an illusion, does that change whether someone deserves blame for a harmful choice or credit for a generous one? Many psychologists have studied exactly this question, and the findings are uncomfortable. In multiple studies, when people were exposed to arguments suggesting free will does not really exist, some of them became measurably more likely to behave dishonestly afterward, as though believing your choices do not truly belong to you quietly loosens your sense of responsibility for them. That alone suggests this is not just a philosophical puzzle floating somewhere far away from daily life. It might be quietly shaping how seriously people take their own actions, whether they realize it or not. So where does this leave you? It leaves you in an uncomfortable but honest place. Brain activity may begin shaping your choices before you consciously notice anything happening. And yet the full picture of who is really doing the choosing, whether it is some isolated flicker of neurons or the entire accumulated weight of your memories, values, and personality acting together as one unified system, remains genuinely unresolved. Free will may not be the clean, simple, fully conscious authorship most people assume it to be. But that does not necessarily mean it is nothing at all. It might simply be something far stranger and far more layered than anyone has fully figured out yet. What is dark matter made of? Look up at the night sky and you are seeing roughly 5% of what is actually out there. Not 5% of the stars you can spot with your eyes, but 5% of everything that exists in the entire universe. The rest, nearly all of it, is something scientists cannot see, cannot touch, and honestly cannot fully explain. They simply call it dark matter, and despite decades of research, some of the smartest physicists alive still do not know what it is actually made of. Here is how strange this gets. Dark matter was not discovered by spotting something new floating in space. It was discovered because something expected was missing. In the 1970s, an astronomer named Vera Rubin was studying how galaxies rotate, watching stars near the outer edges of spiral galaxies move through space. Based on the visible matter in those galaxies, the stars and gas and dust we can actually detect with telescopes, those outer stars should have been moving much slower than the stars closer to the center, the same way planets farther from the sun orbit more slowly than planets closer in. But that is not what she found. The outer stars were moving almost as fast as the inner ones, which should have caused those galaxies to fly apart entirely, unless something invisible was providing extra gravitational pull, holding everything together. There was simply not enough visible matter to explain the gravity actually being observed. This is the part that should genuinely sit uncomfortably with you. Scientists did not invent dark matter because they wanted a mysterious answer. They were forced into the idea because the math refused to work any other way. Multiple independent lines of evidence kept pointing toward the same conclusion. Galaxies rotate in ways that only make sense if invisible mass is present. Light bends around massive objects in space more dramatically than visible matter alone could cause, a phenomenon called gravitational lensing. Even the leftover radiation from the early universe, called the cosmic microwave background, shows patterns that only make sense if dark matter was shaping the structure of the cosmos from almost the very beginning. Three completely different methods, studied by completely different groups of scientists using completely different tools, all kept landing on the same conclusion. Something massive and invisible is out there, making up roughly 27% of the entire universe, dwarfing the 5% made of the ordinary matter that forms stars, planets, and everything you have ever physically touched. So what actually is it? This is where confidence quietly drops off, even among experts. For decades, the leading guess was something called YMPs, which stands for weakly interacting massive particles, theoretical particles that would barely interact with regular matter at all, almost completely ignoring it except through gravity, which is exactly why they would be invisible to every instrument we have ever built. Massive detectors have been constructed deep underground, shielded from interference, specifically designed to catch the rare moment a WMP might collide with normal matter. After years of waiting, watching, and refining these experiments, still nothing definitive has been found. Not a clear detection, not a confirmed signal. That failure has pushed scientists to consider other possibilities, each one stranger than the last. Some physicists suspect dark matter might be made of axions, an entirely different type of theoretical particle, almost unbelievably lightweight, that would behave completely unlike anything in the standard model of physics we currently rely on. Others have proposed that dark matter might not be made of new particles at all, but could instead be leftover primordial black holes, tiny black holes formed in the first fractions of a second after the universe began, too small and too dark to detect directly, yet numerous enough to provide the missing gravity. A smaller group of physicists have gone even further, suggesting that maybe dark matter does not exist as a substance at all, and instead our understanding of gravity itself is slightly wrong at extremely large cosmic scales, meaning the missing mass problem might actually be a missing physics problem. What makes this especially unsettling is the scale of our own uncertainty. This is not some obscure detail buried in a research paper nobody reads. This is roughly a quarter of the entire universe, sitting there, quietly shaping galaxies, bending light, and influencing the large-scale structure of everything that exists, while remaining almost completely undetectable using every method modern science has thrown at it so far. If you find that disturbing, that reaction makes sense. Humans generally feel uneasy not knowing things, especially big foundational things, because uncertainty triggers the same instinctive unease our ancestors felt facing unknown threats in the dark. But dark matter is not a threat sitting somewhere out there waiting to strike. It is simply a reminder of how much of reality remains unmapped, even at the largest possible scale. The universe is not hiding some small obscure detail from us. It is hiding the majority of itself, in plain sight, surrounding every galaxy you have ever seen, and so far, it has not given up the secret of what it is actually made of. What is dark energy, and why is it accelerating the universe? In 1998, astronomers expected to confirm something they were already fairly confident about. They were measuring distant exploding stars, called supernovae, to figure out how fast the expansion of the universe was slowing down, because that is what everyone assumed gravity should be doing, pulling everything back together gradually after the initial expansion from the Big Bang. Instead, they got a result so strange that some of them initially assumed they had made a mistake somewhere. The universe was not slowing down at all. It was speeding up. The expansion of space itself was accelerating, and nothing in known physics at the time could explain why. This discovery won the Nobel Prize in Physics in 2011, and it forced scientists to accept something deeply uncomfortable. Some unknown force, or energy, or property of space itself, was actively pushing galaxies apart faster and faster over time, working directly against gravity at the largest cosmic scales. Scientists needed a name for this mysterious driving force, and since nobody actually knew what it was, they gave it the most honest name they possibly could. They called it dark energy, dark simply meaning unknown, hidden from direct detection, not literally dark in color. Here is where this becomes genuinely difficult to wrap your head around. Dark energy is not a small minor correction to our understanding of the universe. Based on current measurements, dark energy makes up roughly 68% of all the energy and matter in the entire universe. That means the single largest component of all existence is something scientists still cannot directly explain, identify, or detect using any instrument we currently have. You spent your entire life assuming planets, stars, and galaxies were the main event of the universe. In reality, they barely register compared to this invisible force quietly stretching space apart in every direction everywhere, all at once. So what could actually cause this? The leading theoretical explanation involves something called the cosmological constant, an idea that traces all the way back to Albert Einstein himself. When Einstein first developed his equations for general relativity, he noticed something odd. His equations naturally allowed for a kind of built-in energy associated with empty space itself, a constant value that could either push space apart or pull it together depending on its value. At the time, Einstein assumed the universe was static, neither expanding nor contracting, so he added this constant specifically to balance gravity and keep everything stable. Later, when astronomer Edwin Hubble showed that the universe was actually expanding, Einstein removed the constant, reportedly calling it one of the greatest blunders of his career. Decades later, after the accelerating expansion was discovered, scientists realized Einstein's abandoned idea might have been correct all along, just for a different reason than he originally intended. Empty space itself might carry energy, a quiet pressure built into the vacuum of space, constantly pushing outward. But here is the part that makes physicists genuinely uneasy rather than just curious. When researchers tried calculating how much energy empty space should theoretically contain, based on quantum field theory, the numbers that came out were almost absurdly large, dramatically larger than what we actually observe happening in the real universe. By a margin so extreme, it is often described as the worst theoretical prediction in the history of physics. The math says empty space should be exploding with enormous energy. The observed universe shows only a small, specific amount of accelerating push. Nobody has solved why there is such a massive gap between what the equations predict and what reality actually shows. This puzzle does not just sit quietly in academic papers either. It directly determines the long-term fate of everything that exists. If dark energy continues behaving the way it currently appears to, the universe will keep expanding faster and faster, forever, eventually stretching galaxies so far apart from each other that, billions of years from now, the night sky from any single galaxy would appear completely empty, with every other galaxy pulled too far away to ever be seen again. Some physicists call this distant future scenario the Big Freeze, a slow fade into cold isolation, driven by the same mysterious force, currently quietly accelerating everything around you right now, even as you sit completely still reading this. If that idea feels oddly heavy, almost unsettling in a way you cannot quite explain, That reaction makes sense. Human beings are wired to find comfort in stability, in things staying roughly the way they are. Learning that the universe itself is actively being pulled apart by something we cannot identify, name, or fully measure, taps directly into that same discomfort. Even though the actual timeline involved stretches across billions of years, far beyond anything that will affect you personally. So here is where this leaves modern physics. The single largest component of the universe, the very thing currently shaping the ultimate fate of everything that exists, remains almost completely unexplained. Scientists know dark energy is there because of how space behaves. They have given it a name, measured its effects, and calculated its overall share of the universe. But what it actually is, the real underlying mechanism, quietly stretching the fabric of space apart every single moment, remains one of the deepest unanswered questions, standing at the very edge of human scientific understanding. Can multiple universes exist alongside ours? Right now, while you're sitting there watching this, there could be another version of you living a completely different life. Maybe in that life you took the job you turned down. Maybe you said yes to that person you never called back. Maybe you're somewhere else entirely, in a city you've never even visited in this life. Sounds like science fiction, right? Like something out of a movie where the hero jumps between dimensions. But here's the thing. Some of the most respected physicists on the planet, people with decades of research behind them, think this might actually be true. Not as a fun thought experiment, not as a metaphor. They think it might be physically real. Let's slow down for a second, because this gets weird fast. In the early 1900s, scientists were trying to understand how tiny particles behave, things like electrons and photons. And what they found broke everything they thought they knew about reality. A single particle, when it's not being observed, doesn't behave like one thing in one place. It behaves like it exists in multiple states at once. Imagine flipping a coin, and instead of landing on heads or tails, it lands on both at the same time until someone actually looks at it. That's not an exaggeration. That's literally what experiments showed. The particle exists in something called a superposition, a blend of every possible outcome, all happening simultaneously, right up until the moment of observation collapses it down into one single result. Now here's where it gets even stranger. A physicist named Hugh Everett looked at this problem in the 1950s and asked a question nobody wanted to ask. What if the particle doesn't actually collapse into one outcome? What if instead every single possible outcome actually happens, just in separate, branching realities? In his theory, when that coin lands, the universe doesn't pick heads or tails. Instead, the universe splits. In one branch, it's heads. In another branch, it's tails. Both versions are equally real. Both versions exist. They just can't see each other anymore. Sit with that for a second. Every time a quantum event happens, anywhere, the universe could be branching into separate versions of itself. And quantum events are happening constantly, every single second, inside your body, inside the air around you, inside every star in the sky. If Everett was right, the number of parallel universes being created right now isn't in the millions, or even the billions. It's almost incomprehensibly large. Every choice you almost made but didn't. Every coin flip. Every decision point in your entire life. Somewhere, in another branch of reality, the other version happened instead. You're probably thinking this sounds like something a guy on the internet made up to sell a course. But this isn't fringe science. This interpretation known as the many worlds interpretation, is taken seriously by physicists at places like Oxford and Caltech. Surveys of physicists working specifically on the foundations of quantum mechanics show a significant portion of them lean toward this exact explanation, not because it's comforting, but because mathematically, it's actually one of the simplest explanations for what we observe. It doesn't require some mysterious collapse that nobody can fully explain. It just requires accepting that reality is bigger than what we personally experience. And it's not only quantum physics pointing in this direction. Cosmologists studying the early universe ran into a separate but eerily similar idea. The leading theory of how our universe began, called inflation, suggests that in the first fraction of a second after the Big Bang, space expanded so violently fast that it could have kept expanding in different regions at different rates, forever, in different pockets that we can never observe. Each of those pockets could have cooled down into its own universe, with its own physical laws, its own version of gravity, its own version of everything. Our entire observable universe, every galaxy, every star you've ever seen in the night sky, might just be one tiny bubble floating among an endless ocean of other bubbles we will never be able to reach or see. So you've got two completely different fields of science, quantum mechanics and cosmology, arriving at versions of the same unsettling idea from two totally different directions. That's not something you can easily wave away as a coincidence. When separate branches of physics keep bumping into the same strange conclusion, it usually means there's something real underneath it, even if we don't fully understand it yet. If you've ever made a decision and immediately felt this gnawing what-if feeling, wondering what would have happened if you'd chosen differently, you're not just being anxious or overthinking it. You might be brushing up against something real about the structure of existence itself. That feeling of an alternate path tugging at the back of your mind could be the closest thing we have to actual evidence, not proof, but a strange kind of intuition lining up with the math, which raises a question most people never even think to ask. If other versions of you really exist, living out every choice you never made, are they happier than you? Are they more successful, more fulfilled, living the life you secretly wish you had? Or did some of them make even worse decisions, and right now, in some other branch of reality, a different version of you is sitting somewhere wishing they were you instead? Why do the constants of nature appear fine, tuned for life? Picture someone handing you the control panel for an entire universe before it gets switched on. In front of you are dozens of dials. One controls how strongly gravity pulls things together. One controls how tightly the particles inside an atom bond. One controls how fast space itself expands. You're told you have to set every single dial correctly before flipping the switch, and you only get one attempt. Now picture the margin for error on most of those dials. It isn't generous. It isn't even small. On some of them, the margin is so razor thin that nudging the dial by an amount smaller than anything you could ever picture would mean nothing in that universe ever forms. No stars, no atoms heavier than hydrogen, no planets, no life of any kind. And somehow, when our actual universe came into existence, every single one of those dials landed exactly where it needed to be. Take gravity as the first example. If gravity were just a tiny bit stronger than it actually is, stars would burn through their fuel so fast they would collapse within a few million years, long before anything like a planet could cool down and stabilize. If gravity were just a tiny bit weaker, gas clouds in the early universe would never have had enough pull to clump together into stars at all. You would just have an endless, thin fog drifting through empty space forever. The actual strength of gravity sits inside a window, so narrow that physicists describe it less like a range and more like a single point. Now look at the force holding the nucleus of an atom together, the one responsible for fusing hydrogen into helium inside stars. If that force were turned up by even a fraction of a percent, hydrogen would have fused into helium almost instantly after the Big Bang, leaving the universe with no hydrogen left over. No hydrogen means no water, and water is the foundation almost every theory of life depends on. If that same force were turned down by a similarly tiny amount, atomic nuclei would never bond at all, and stars would never ignite in the first place. There is a famous case involving carbon, the element every known form of life is built from. For carbon to form in any meaningful quantity inside a star, the internal energy levels of the nucleus need to line up almost perfectly. Physicist Fred Hoyle predicted this exact alignment had to exist before anyone had even confirmed it experimentally, purely because he ran the numbers and realized that without it, carbon simply could not exist in the universe in large enough amounts for anything resembling life to ever form. Then, there is the expansion rate of the universe itself, tied to something called the cosmological constant. This number determines how fast space stretches apart over time. If you nudged this constant up or down by an amount so small it would take more zeros to write out than there are atoms in every star you can see in the night sky combined, the universe would have either blown itself apart before a single galaxy could form, or collapsed back in on itself within moments of the Big Bang. Either way, nothing like us would ever exist to ask why. You'd think a coincidence stacked on top of another coincidence, stacked on top of dozens more, would eventually break under its own weight. And that exact thought is what pushed serious physicists, not casual commentators but people who spent their careers studying this, to take the question seriously instead of brushing it aside. This is officially known among scientists as the fine-tuning problem, and there is genuine, ongoing disagreement about what it actually means. One camp argues this is exactly what you would expect if there are countless other universes out there, each with its own random set of dial settings, most of them lifeless and forever empty. Under that view, we are not lucky so much as we are the only ones capable of noticing we exist, because every other version of this experiment failed silently, with nobody around to observe it. This is sometimes called observer selection. You only ever find yourself in the universe capable of producing you. Another camp looks at the same evidence and reaches a very different conclusion, arguing that the precision is itself a sign of deliberate design rather than chance, the same way finding a working watch on a beach suggests a watchmaker rather than random erosion. And a third camp suspects we are simply missing a deeper law of physics, one that hasn't been discovered yet, that would reveal these constants were never actually free to be anything other than what they are. The same way you eventually realize a magic trick was never magic to begin with once you learn how it works. None of these three explanations has been proven. Each one has serious, credentialed defenders who can argue their case with real evidence behind it, and each one has equally serious critics who can poke real holes in it. What almost nobody disputes, regardless of which camp they fall into, is the underlying observation itself. The numbers really are absurdly precise. The dials really do appear set with a level of accuracy that has no obvious reason to exist. So you're left holding the same unsettling question physicists have been sitting with for decades. Are you the product of a freak accident, so improbable it shouldn't have happened, even once, repeated across more failed universes than you could ever count, with you simply standing in the one that worked? Or is the precision itself trying to tell you something else entirely, something nobody has quite figured out how to prove yet, one way or the other? What causes quantum events to become definite outcomes? There is an experiment that has been run thousands of times over the last 100 years, in dozens of different labs, using completely different setups, and it still produces a result that makes seasoned physicists uncomfortable. Take a single particle of light, a photon, and fire it at a wall that has two narrow slits cut into it. Behind that wall is a screen that records where each photon lands. If you fire thousands of these photons one at a time, and nobody watches which slit they actually pass through, the photons land on the screen in a pattern that only makes sense if each individual photon somehow traveled through both slits at once and interfered with itself on the way through, like a wave splitting and rejoining. Stripes show up on the screen, alternating bands of light and dark, the exact signature you would expect from two overlapping waves. But here is where it turns from strange to almost unbelievable. The moment you place a detector at the slits to actually check which one each photon goes through, the interference pattern vanishes completely. The photons start behaving like a wave and start behaving like a normal particle, landing in two simple clumps, one behind each slit, exactly like a tiny ball would. Sit with that for a second, because it is not a metaphor and it is not an analogy. The simple act of checking, of gaining information about which path the particle took, physically changes the outcome of the experiment. Nothing about the photon itself changed. No force was applied to it. The only thing that changed was whether or not the information about its path existed somewhere in the universe. And that single fact has haunted physics for over 100 years, because the equations that describe quantum particles, the actual mathematics, never predict a single definite outcome. They only predict a smooth, continuous spread of probabilities, every possible outcome layered on top of every other one, all the way up until somebody measures it. At that exact moment, and nowhere written into the math, the spread collapses down into one single, definite result. Nobody has ever written an equation that tells you precisely when or why that collapse happens. It just does, every single time, and the math has no explanation for the mechanism behind it. Erwin Schrödinger, one of the founders of quantum theory, was so unsettled by this that he came up with a thought experiment specifically designed to show how absurd the implications were. Imagine sealing a cat inside a box along with a radioactive atom that has a 50% chance of decaying within an hour. If the atom decays, it triggers a mechanism that releases poison and kills the cat. If it doesn't decay, the cat lives. According to the raw mathematics of quantum theory, until you open the box and check, the atom exists in a blend of both decayed and not decayed at the same time, which technically means the cat inside is described as both alive and dead simultaneously, not as a 50-50 guess, but as an actual mathematical superposition of both states. Schrödinger wasn't proposing this as something he believed literally happened to the cat. He was pointing out that something in the theory has to be incomplete, because cats obviously don't exist in two states at once in the real world. Yet the math says they should, right up until an observation forces one outcome to become real. This is officially called the measurement problem, and it remains one of the most actively debated topics in physics departments around the world. Not because physicists are confused about how to use the equations. They use them constantly to build working technology like lasers and computer chips, but because nobody agrees on what is physically happening underneath those equations at the exact moment of collapse. One leading explanation, called decoherence, suggests that the particle never really collapses in some mysterious instant at all. Instead, the particle's delicate quantum state leaks out and tangles with the huge number of particles in its environment, the air, the detector, the measuring equipment, so quickly and so thoroughly that the original superposition becomes practically impossible to detect again, even though in some deeper mathematical sense it technically still exists, smeared out across everything it touched. Decoherence explains why we never see large objects like cats or coffee cups sitting in two places at once. But critics point out that decoherence still doesn't fully explain why you, the observer, only ever experience one single outcome instead of experiencing the blurred mixture of all of them. Some of the most respected names in 20th century physics admitted openly that this part of the theory simply isn't understood yet, despite the theory itself being one of the most accurately tested in the history of science. That combination is what makes this question so unusual. It isn't a case of bad data or sloppy thinking. The predictions of quantum mechanics have been confirmed to an almost absurd level of precision, again and again, in experiment after experiment. And yet the most basic question you could possibly ask about it, why does a measurement turn a spread of possibilities into one single fact, still does not have an agreed upon answer. So the next time you glance at your phone and a notification appears, or you check the time and see one specific number on the clock, consider that on some fundamental level, underneath all of it, physics still cannot fully explain why you got one definite reality instead of an overlapping blur of every possibility at once. It just knows, with extreme precision, that somehow, every single time, you do. Is space fundamentally continuous or made of tiny units? Open a photo on your phone and zoom in. At first the image stays sharp, the edges stay smooth, everything still looks like a real scene. But keep zooming, and at some point the picture stops being a picture at all. It dissolves into a grid of tiny colored squares, individual pixels, the actual smallest building blocks the image was ever made of. There was never a smooth photo underneath it waiting to be revealed. The smoothness was an illusion created by your eyes being too far away to notice the grain. Now ask yourself an uncomfortable question. If you zoomed into empty space itself, the actual fabric of the universe between 2 points, far enough, would you eventually hit a similar floor? Would space dissolve into tiny individual units that cannot be divided any further? Or would it stay smooth and continuous forever, no matter how far down you zoomed, with no floor at all? This isn't just a fun riddle. It might be one of the most important unanswered questions in all of physics, because our two best theories of how the universe works flatly disagree on the answer. General relativity, the theory that describes gravity and the large-scale structure of the cosmos, treats space as a smooth, continuous fabric that can bend and stretch without limit, like an infinitely flexible sheet of rubber with no minimum size at all. Quantum mechanics, the theory that describes particles and forces at the smallest scales, suggests almost everything in nature comes in discrete chunks. Energy comes in chunks. Light comes in chunks called photons. Even the spin of a particle only ever takes specific allowed values, never anything in between. So, which one of these two enormously successful theories is right about the nature of space itself? Right now, nobody fully knows, and the deeper physicists dig, the stranger the answer seems to get. Here's where it gets genuinely unsettling. Physicists calculated a specific length, named the Planck length after the physicist Max Planck, that represents the smallest distance where our current laws of physics still make any sense at all. It is almost impossible to describe how small this distance actually is. If you took a single atom and blew it up to the size of the entire observable universe, the Planck length on that same scale would still only be about the size of a small tree. Below that threshold, the smooth equations of general relativity and the probabilistic equations of quantum mechanics stop agreeing with each other entirely. Space and time, instead of behaving like a calm, predictable backdrop, are predicted to violently froth and bubble, with tiny regions popping in and out of existence faster than you could ever measure them. Physicist John Wheeler gave this idea a name that stuck, calling it quantum foam, a chaotic, churning structure underlying everything we experience as smooth, stable, empty space. One major group of physicists, working on something called loop quantum gravity, takes this seriously enough to build an entire theory around it. Their math suggests that space isn't a continuous backdrop at all, but is instead woven out of incredibly tiny individual loops, almost like threads stitched together into a fabric, where area and volume themselves only come in specific, discrete amounts, the same way money only comes in specific denominations, and you can never hand someone half a cent. Under this view, there is a genuine smallest possible unit of space, a literal floor beneath which the question of smaller distance stops meaning anything, because there simply isn't anything smaller for it to refer to. Other physicists, working from a completely different framework involving vibrating strings, end up with smooth, continuous space surviving at the deepest level, with the apparent graininess showing up somewhere else in the math instead. Two serious, mathematically rigorous approaches built by brilliant people who have spent entire careers on this, and they don't agree on something as basic as whether space can be cut in half forever, or whether it eventually stops. What makes this more than empty philosophical debate is that scientists have actually figured out a way to test for it using something happening across the universe right now. When extremely violent cosmic events, like massive stars collapsing, send out bursts of gamma radiation, that light has to travel across billions of light years to reach our telescopes. If space really is grainy at the tiniest scale, then photons with different energies should be very slightly slowed down by different amounts as they pass through that graininess, the same way wading through gravel slows you down more than wading through sand. Over a short distance, that tiny difference would be far too small to notice. But stretched across billions of light years, it should add up into a measurable, detectable delay between when higher energy and lower energy light from the same explosion actually arrives. Telescopes like the Fermi Gamma Ray Space Telescope have actually gone looking for that delay in real cosmic explosions, hoping to catch space itself in the act of being grainy. So far, the results haven't given a clean answer either way. Some signals have hinted at tiny delays consistent with a grainy universe. Others have come back essentially flat, more consistent with space staying smooth all the way down. The experiments keep getting more sensitive, and the question keeps refusing to fully resolve itself, which leaves you with something genuinely strange to consider the next time you watch something move smoothly across a room. That motion might be exactly what it appears to be, a continuous flow through an infinitely divisible space. Or it might secretly be something closer to a film reel, a rapid sequence of distinct, individual frames stitched together so tightly that nothing in your entire life has ever moved slowly enough for you to notice the gaps. Why is there a physical reality at all? Most people never stop to ask this question, not because it is unimportant but because reality feels too obvious to question. You wake up. You touch the floor. You feel the weight of your body. You look outside and see buildings, trees, clouds, people. Reality seems so normal that it almost disappears into the background. But think about this for a second. Why is there anything at all? Not why does Earth exist? Not why does life exist? Why does physical reality itself exist? The moment you seriously ask that question, something strange happens. The entire world around you starts feeling less solid than it did a minute ago. Because every explanation we normally use eventually hits a wall. Imagine asking where a river comes from. Someone points to a mountain. You ask where the mountain came from. They point to geological forces. You ask where those forces came from. They point to the formation of planets. You keep asking. Eventually, you reach the beginning of the universe itself. And then what? What created that? This is where things become deeply uncomfortable. Modern science has done an incredible job explaining how reality behaves. It can describe gravity, atoms, stars, black holes, and even the earliest moments after the Big Bang. But when it comes to why there is a physical reality in the first place, science reaches a boundary. Because explaining how something works is very different from explaining why it exists at all. The Big Bang is often treated as the beginning of everything. But even if the universe began with the Big Bang, the question still remains. Why was there a Big Bang instead of nothing? And what exactly is nothing? At first that sounds simple. Nothing means nothing, no matter, no energy, no space, no time. But the more philosophers and physicists examine the idea, the stranger it becomes. Because maybe true nothingness is impossible. Think about it. We can imagine an empty room, but the room still exists. We can imagine empty space, but space still exists. We can imagine darkness, but darkness is still something. True nothingness is almost impossible for the human mind to picture. And that creates a disturbing possibility. What if existence is not the thing that needs explaining? What if non-existence is the impossible state? That sounds backwards because every instinct tells us that nothing should be simpler than something. Yet some thinkers argue the opposite. They suggest reality exists because reality cannot fail to exist. But even that answer raises more questions than it solves. Because if existence is necessary, why does it take this particular form? Why this universe? Why these laws of physics? Why matter instead of something completely different? The numbers governing reality are so precise that even tiny changes could have produced a universe where stars never formed, planets never existed, and life was impossible. Some scientists point to the possibility of multiple universes. In this view, there may be countless realities with different rules, and we happen to exist in one capable of supporting observers, but that explanation creates its own mystery. If there are countless universes, what created the system that allows countless universes to exist? The question simply moves one level deeper, and this is where many people begin to feel a strange sense of vertigo. It is the feeling that every answer sits on top of another question, like standing between two mirrors and watching reflections stretch endlessly into the distance. No final foundation ever appears. Human beings are not comfortable with that. Our brains evolved to solve practical problems, find food, avoid danger, build shelter. We naturally assume every effect has a cause because that assumption helps us survive. But when we apply that same logic to reality itself, we encounter something that may not fit inside ordinary human understanding. Maybe reality had a beginning. Maybe it never began. Maybe time itself emerged from something outside time. Maybe there is a deeper level of existence beneath everything we can observe. Or maybe the human brain simply lacks the tools to fully grasp the answer. That last possibility is easy to dismiss, but think about it. A dog can learn commands. It can recognize faces. It can solve simple problems. But there are concepts a dog will never understand, not because it is not trying hard enough. Its brain is simply not built for them. Now ask yourself a frightening question. What if humans are the same way? What if the ultimate reason for existence lies beyond the limits of human cognition? What if we are asking a question that our minds were never designed to answer? The unsettling part is that we may never know, and yet the mystery refuses to disappear. Every object you touch, every person you love, every memory you carry, every star in the night sky exists within a reality whose existence remains fundamentally unexplained. We have mapped continents, split atoms, landed on the moon, and built machines capable of extraordinary calculations. Yet one of the most basic questions imaginable still stands untouched at its core. Why is there something rather than nothing? The fact that reality exists at all may be the greatest mystery we have ever encountered. Not because nobody has tried to answer it, but because every answer seems to reveal an even deeper question waiting underneath. And somewhere beneath all the noise of everyday life, beneath work, goals, routines, and distractions, there is a quiet realization that never completely goes away. You are here. The universe is here. Reality is here. And nobody truly knows why. Right now, as you listen to this, information is flowing through you. Not just words. Information. Your eyes are taking in light. Your ears are processing sound. Your brain is constantly decoding patterns, sorting signals, and constructing meaning from an endless stream of data. Every thought you have, every memory you recall, every decision you make depends on information. But here is the strange part. Nobody can fully agree on what information actually is. We use the word every day. We talk about information as if it is obvious. Yet when you look closely, it becomes one of the most mysterious things in existence. Think about a simple book. At first glance, it seems like information lives inside the pages. But the pages are just paper. The ink is just chemicals arranged in shapes. If someone cannot read the language, the information disappears. The symbols remain, but the meaning vanishes. So where was the information really located? In the paper. In your mind. Or somewhere in the relationship between all of them. The deeper you go, the stranger it becomes. Imagine two people looking at the exact same set of symbols. One sees random marks. The other sees a story that changes their life. The physical object is identical. The atoms are identical. Yet the informational reality is completely different. That should make you pause, because it suggests information is not quite the same thing as matter. It is not quite the same thing as energy either. In fact, Information seems to exist in a category all its own, and modern science keeps running into that mystery. For centuries, physicists believed matter was the fundamental building block of reality. Everything was ultimately particles and forces. Then something unexpected happened. The more scientists studied nature, the more information seemed to move toward the center of the picture. Take DNA. A strand of DNA is made from ordinary molecules. Nothing magical about the chemicals themselves. What matters is the arrangement. Change the pattern and you change the organism. The information encoded in the sequence becomes more important than the material carrying it. The same principle appears in computers. Your favorite movie, a family photograph, a song, and a scientific paper can all exist on the same storage device. Physically, they are just arrangements of electrical states. What makes them different is not the hardware. It is the information, and that raises an unsettling possibility. What if information is more fundamental than the physical objects that store it? Some physicists have seriously explored this idea. They have noticed that reality often behaves less like a collection of objects and more like a network of information being processed. Quantum physics pushes this idea into even stranger territory. At the quantum level, particles do not always seem to possess definite properties until measurements occur. Instead of behaving like tiny solid objects, they often appear as probabilities and informational possibilities. That sounds almost impossible, because we instinctively believe the world is made of things, tables, mountains, planets, bodies. But what if those things are not the deepest layer? What if the deepest layer is information itself? Imagine a video game. Inside the game, characters see buildings, roads, weather, and landscapes. Everything appears physical from their perspective. Yet beneath the entire world lies code. The visible reality emerges from information being processed underneath. Now imagine reality itself operating in a similar way. Not necessarily as a literal simulation, but as something where information sits at the foundation and physical objects emerge from it. Suddenly, matter stops being the starting point. It becomes the result. And that possibility changes everything. Because if information is fundamental, then reality may be less like a machine and more like a language, less like a collection of objects and more like a system of relationships and patterns. Even black holes have forced scientists to confront this mystery. For decades, researchers struggled with a problem known as the black hole information paradox. The issue was surprisingly simple. If information falls into a black hole and disappears forever, then one of the most important principles in physics appears to break down. The laws governing reality seem to insist that information cannot simply vanish. Think about how bizarre that is. Matter can change form. Stars can explode. Galaxies can collide. Yet information appears to possess a special status, as if reality itself is protecting it. Nobody fully understands why, and the mystery extends beyond physics. Human consciousness creates another layer of confusion. Right now, your memories exist as patterns of information. Your identity is tied to information. Everything you believe yourself to be depends on information stored and processed within your brain. If every memory were removed, would you still be the same person? Most people instinctively say no, which means information is not just something you possess. In a very real sense, information is part of what you are. That realization can feel unsettling, because it blurs the line between physical existence and abstract existence. A memory has no weight. A mathematical truth occupies no space. A story cannot be touched. Yet all of these things can shape reality. Entire civilizations have risen and fallen because of information. Wars have started because of information. Lives have been transformed because of information. Something that seems intangible somehow possesses enormous power, and nobody has fully explained why. Maybe information is simply a useful human concept. Maybe it is a property of physical systems, or maybe it is something far deeper, something woven into the fabric of existence itself. The truth is that we still do not know. We know information can be stored. We know it can be transmitted. We know it can shape reality in profound ways. But we still cannot confidently answer one fundamental question. What exactly is information? Is it merely a description of reality? Or is it one of reality's most basic ingredients? If the second possibility is true, then everything around you may be far stranger than it appears. Because beneath every atom, every star, every living creature, and every thought inside your mind, there may exist a deeper layer, made not of matter or energy, but of information itself. And if that is the case, then understanding information may ultimately mean understanding reality. Can reality exist independently of observation? Take a moment and imagine an empty room. No people, no cameras, no animals, no sensors. Nothing capable of seeing, hearing, measuring, or recording anything. Now ask yourself a simple question. Does that room still exist? Most people answer immediately. Of course it does. The room does not need anyone looking at it to remain real. It feels obvious. Almost too obvious to question. But the moment you begin examining that assumption, one of the deepest mysteries in science and philosophy opens beneath your feet. Because how do you actually know reality exists when nobody is observing it? At first, the question sounds ridiculous. After all, the world seems to continue without us. Cities remain standing while we sleep. Oceans keep moving. Stars continue burning millions of light years away. Reality appears perfectly capable of existing on its own. Yet every piece of evidence you have ever collected about reality shares one unavoidable feature. You observed it. Everything you know about the universe comes through observation. Every scientific experiment, every measurement, every photograph, every memory, every fact you believe about the world, all of it arrives through some form of observation. And that creates a strange problem. We are trying to determine whether reality exists independently of observation, using tools that depend entirely on observation. It is like trying to see your own eyes without using a mirror. The very act of investigating the question seems trapped inside the thing we are questioning. For centuries, most people never worried much about this. Reality simply appeared to exist, whether anyone looked at it or not. Then quantum physics arrived and complicated everything. In the everyday world, objects seem to possess definite properties. A ball is here. A chair is there. A tree exists whether someone sees it or not. But at the quantum level, things become deeply unsettling. Experiments suggest that tiny particles often behave less like solid objects and more like collections of possibilities. Instead of having one definite state, they appear capable of existing in multiple potential states simultaneously. Then something happens. A measurement is made, an observation occurs, and one outcome appears. This idea has confused scientists for generations, because it sounds dangerously close to saying observation creates reality. And if that were true, the implications would be enormous. Imagine a coin spinning in the air. Common sense says it is either heading toward heads or tails even before it lands. Quantum physics suggests reality may not always work that way. In some situations, nature seems to keep multiple possibilities open until an interaction forces a specific outcome. The famous double-slit experiment became one of the most shocking demonstrations of this idea. When particles pass through two openings without being measured, they behave like waves spreading through multiple possibilities. When measurements are introduced, they begin behaving like particles taking specific paths. The details are incredibly complex, but the emotional impact is simple. Reality appears to behave differently when observation enters the picture. That realization has inspired decades of debate. Some people interpret these experiments as evidence that consciousness plays a direct role in creating reality. Others strongly disagree. Many physicists argue that observation does not necessarily mean a conscious mind looking at something. Instead, any interaction with the environment may count as a measurement. The disagreement continues because the underlying mystery remains unresolved. Nobody fully agrees on what is actually happening beneath the mathematics, and that uncertainty creates an uncomfortable possibility. What if reality is not as independent as we assume? Think about your own experience. Right now, everything you know exists within awareness. The room around you exists because you perceive it. The sounds you hear exist because your brain processes them. Even your understanding of the universe exists inside conscious experience. You have never directly stepped outside observation itself. Nobody has. Every human being experiences reality through a window they can never leave. And yet most of us rarely think about that. We assume there is a complete external world existing exactly as it appears. Maybe there is. But can we ever prove it? Philosophers have wrestled with this question for thousands of years. Some argued that an external reality exists independently of our minds. Others suggested that what we call reality may be inseparable from perception itself. Neither side has achieved a final victory, because every argument eventually runs into the same obstacle. The only reality we ever encounter is experienced reality, and that leaves a gap between what exists and what can be known. Modern neuroscience adds another twist. Your brain is not passively recording reality like a camera. It actively constructs your experience. Colors do not exist in the outside world the way you experience them. Sound does not exist as sound until your brain interprets vibrations. Even your sense of space and time emerges from neural processing. The reality you experience is already a kind of internal model, a useful one, a remarkably accurate one, but still a model. This means that what feels like direct contact with reality may actually be your brain's best interpretation of something deeper, something hidden beneath perception. And if that is true, then the question becomes even more mysterious. Are we observing reality itself, or are we observing a representation generated by our minds? The distinction matters, because if all experience is filtered through observation, then reality may always remain partly beyond our reach. Not because it is absent, but because we can never access it without interpretation. Yet despite all these uncertainties, something remarkable remains true. Reality consistently behaves as if it possesses structure independent of us. The laws of physics do not seem to change according to personal beliefs. Planets continue orbiting stars whether anyone notices them or not. The universe displays a stability that strongly suggests something exists beyond individual observers. And still, the deepest question refuses to disappear. Does reality exist completely on its own? Or does observation play a more fundamental role than we currently understand? After centuries of philosophy and decades of scientific investigation, nobody has produced a definitive answer. The mystery remains open. Perhaps reality stands entirely independent of observation. Perhaps observation is woven into the fabric of existence itself. Or perhaps the truth lies somewhere between those extremes, in a place our current understanding cannot yet reach. What makes the question so powerful is not that it has no answer. It is that every attempt to answer it forces us to confront something we usually ignore. The fact that everything we know about reality arrives through observation. And no matter how far we push our understanding of the universe, we can never completely escape that fact. Is the universe infinite or finite? Stand outside on a clear night and look up. For a moment, try to ignore everything you know. Forget the names of the stars. Forget galaxies, planets, and scientific theories. Just stare into the darkness and ask yourself one question. How far does all of this go? Not how far can we see. How far does reality itself extend? Most people have a gut reaction. The universe feels endless. The night sky stretches in every direction, and our minds naturally imagine it continuing forever. But then another thought appears. What if it does not? What if somewhere, impossibly far away, the universe actually ends? The moment you seriously consider either possibility, your intuition begins to break apart. Because both answers sound impossible. An infinite universe sounds absurd. A finite universe sounds absurd. And yet one of them may be true. This is what makes the question so fascinating. No matter which answer you choose, your brain struggles to hold on to it. Start with infinity. Imagine traveling through space forever. You pass stars, galaxies, clusters of galaxies, and vast regions of darkness. Millions of years pass, then billions, then trillions. But no matter how far you travel, there is always more space ahead, no edge, no boundary, no final destination. Just endless extension. At first that sounds simple enough, but think carefully about what infinity actually means. An infinite universe would contain an unlimited amount of space, potentially an unlimited number of stars, potentially an unlimited number of planets, and if the laws of physics remain consistent throughout that infinite expanse, something strange begins to happen. Given enough space, every possible arrangement of matter could eventually repeat. Some physicists have pointed out that in a truly infinite universe, there could be regions where particles are arranged exactly like they are here, right now. Which means somewhere unimaginably far away, there could be another Earth, another version of this moment, another version of you. Not because of magic, not because of destiny, simply because infinity allows every possibility enough room to occur. The idea sounds like science fiction, yet it emerges naturally from certain interpretations of an infinite cosmos. And that is where infinity begins to feel less like an answer and more like a mystery, because the consequences become almost impossible to comprehend. But now consider the alternative. What if the universe is finite? At first that sounds more reasonable. After all, most things we encounter have limits. A book has a final page. A road has an end. A room has walls. Why should the universe be different? Yet the moment you imagine a finite universe, another problem appears: what lies beyond it? This question arrives almost automatically. If the universe ends somewhere, what exists on the other side? More space, another reality, absolute nothingness. Every option feels confusing, because if there is something beyond the boundary, then the universe was not truly the whole universe. And if there is nothing beyond it, what does that even mean? Human intuition struggles with edges, especially when discussing reality itself. Interestingly, modern cosmology offers a possibility that sounds bizarre but may help explain the problem. A finite universe does not necessarily need an edge. Think about the surface of Earth. If you start walking in one direction, you never encounter a boundary. You do not reach a wall where the planet suddenly stops. Instead, you eventually return to where you started. The surface is finite because it contains a limited area, yet it has no edge. Some scientists suggest the universe could work in a similar way, not as a flat space with boundaries, but as a higher dimensional structure that curves back on itself. In such a universe, space could be finite while still lacking an outer border. You could theoretically travel forever without finding an end. Not because space is infinite, but because it loops in a way your everyday intuition was never designed to understand. That possibility sounds strange because evolution never prepared our brains for cosmic geometry. Our ancestors needed to understand forests, rivers, and predators, not the shape of space-time. And yet observations of the universe have forced scientists to consider these extraordinary ideas. Measurements of cosmic expansion suggest the universe is incredibly large, far larger than the portion we can directly observe. In fact, the observable universe is only the region whose light has had time to reach us since the beginning of cosmic expansion. Beyond that horizon may exist vast regions we will never see, not because they are hidden, but because light from them cannot reach us. This creates an important distinction. The observable universe is finite, but the entire universe may be much larger, possibly even infinite. The truth is that current observations cannot yet provide a definitive answer. Data suggests space appears remarkably flat on large scales. That finding is significant because perfectly flat geometry is consistent with an infinite universe. However, an enormous finite universe can appear flat as well, just as Earth's surface appears flat when viewed from a small enough area. From our perspective, the difference can be extraordinarily difficult to detect, which means one of humanity's greatest questions remains unresolved. The universe may stretch forever, or it may possess a hidden shape that closes in on itself. Both possibilities remain alive, and both reveal something profound about the limits of human understanding. Because this is not merely a question about astronomy. It is a question about the nature of reality itself. Can existence be truly endless? Can something have limits without edges? Can space curve in ways that completely defy common sense? The deeper you explore the mystery, the more you realize how small everyday intuition really is. Our minds crave simple pictures, a beginning, an ending, a boundary, a final answer. But the universe does not seem obligated to satisfy those expectations. Perhaps reality is infinite beyond comprehension. Perhaps it is finite in a way we cannot easily visualize. Or perhaps the true structure of the cosmos is stranger than either possibility. For now, all we can say with confidence is this. Somewhere beyond the stars, beyond the galaxies, beyond every horizon we can observe, the answer already exists. The universe knows whether it is finite or infinite. The mystery is that we still do not. Imagine walking into your bedroom after a month without cleaning it. Clothes are scattered across the floor. Books are piled in random places. Dust has settled on every surface. The room looks completely different from the day you organized it. Now ask yourself something simple. When was the last time you walked into a messy room and found that it had somehow cleaned itself? Not partially, not by accident, completely. Clothes folded, dust gone, everything perfectly organized. The answer is obvious. Never. And that tiny everyday observation points toward one of the deepest mysteries in all of reality. Why does disorder seem to increase? Why does the universe have a preferred direction? Why does everything appear to move from order toward chaos and never the other way around? This idea sits at the heart of entropy. And despite how often the word is used, entropy is one of the most misunderstood concepts in science. Most people hear entropy and think it simply means disorder. That is useful as a starting point, but the real story is much stranger. Imagine you have a deck of cards arranged perfectly by suit and number. Every card is exactly where it belongs. Now shuffle the deck. After enough shuffling, the cards become mixed in countless possible arrangements. The interesting part is not that order disappeared. The interesting part is that there are vastly more mixed arrangements than organized ones. A perfectly ordered deck represents a tiny number of possible states. A shuffled deck represents an enormous number of possible states, and that is the key. Entropy is not really about messiness, it is about probability. The universe naturally moves toward states that can exist in more possible ways. And once you understand that, everyday reality starts looking completely different. Think about dropping an ice cube into a glass of warm water. The ice melts. The cold spreads out. Eventually, everything reaches roughly the same temperature. What never happens is the reverse. You never see warm water spontaneously separate itself into hot and cold regions while rebuilding the ice cube. Not because the laws of physics forbid it. This is where things become shocking. At the microscopic level, the individual particles do not care about the direction of time. The equations governing their behavior often work just as well forward as backward. In theory, the melted ice could reassemble itself. The particles could reverse their motion. The water could freeze. The process is not impossible according to the fundamental laws. It is simply unimaginably improbable. The number of ways particles can exist as mixed water is overwhelmingly larger than the number of ways they can exist as a neatly formed ice cube. So reality almost always moves toward the more probable state. And when you realize that, an unsettling question emerges. If the laws of physics do not strongly distinguish between past and future, then why does time itself feel directional? Why do we remember yesterday but not tomorrow? Why do eggs break but never unbreak? Why does aging move in only one direction? The answer appears deeply connected to entropy. In fact, many physicists believe entropy is the reason time feels like it flows forward at all. Think about your memories. Every memory you possess is a record of a lower entropy state becoming a higher entropy state. You remember a glass before it shattered. You remember a building before it crumbled. You remember being younger before growing older. Your entire experience of time may be tied to the increasing entropy of the universe. Without that increase, the distinction between past and future could become meaningless. That realization changes the question completely. Entropy is not merely something happening inside the universe. It may be helping define our experience of reality itself. But this creates an even bigger mystery. Why was entropy low to begin with? Because if entropy naturally increases, then the early universe must have started in an extraordinarily ordered condition, and that fact has puzzled scientists for decades. The universe that emerged after the Big Bang was not random chaos. In a very important sense, it possessed remarkably low entropy. That initial condition is what allowed stars to form, galaxies to emerge, planets to develop, life to exist, and eventually, conscious beings capable of asking questions about entropy. But why did reality begin that way? Why was the starting point so special? Nobody knows, and this is where one of the biggest unanswered questions in physics appears. We understand how entropy increases. We understand the mathematics behind it. We understand why probability favors it. What we do not understand is why the universe began in a state that made entropy increase possible in the first place. It is like opening a mystery novel and discovering that the first page has been torn out. The story makes sense moving forward, but the crucial beginning remains missing. Some physicists have proposed that our universe emerged from a deeper process that naturally produces low entropy beginnings. Others suggest there may be multiple universes, with ours being one region in a larger cosmic system. Still others believe an entirely new framework of physics may be required to explain the mystery. For now, no explanation has achieved universal acceptance, and the implications extend far beyond science. Because entropy touches every part of existence, stars burn their fuel and eventually die. Mountains erode, civilizations rise and fall, memories fade, bodies age. Everything familiar exists within this vast tendency toward increasing entropy. It is woven into the fabric of daily life so deeply that we rarely notice it. Yet without it, reality would look completely different. There would be no meaningful distinction between before and after, no clear direction of time, no unfolding history, no experience of change as we know it. That is what makes entropy so fascinating. At first glance, it seems like a technical concept hidden inside physics textbooks. But underneath, it may be one of the fundamental reasons reality appears the way it does. The reason broken things stay broken. The reason the past feels different from the future. The reason time seems to move relentlessly forward. And perhaps most mysterious of all, the reason the universe began in a condition that allowed any of this to happen in the first place. The laws of physics can describe entropy with astonishing precision. But the deeper question remains unanswered. Not why entropy increases, but why reality was ever arranged in a way that made its increase inevitable. What determines the arrow of time? Every second of your life is built around an assumption so obvious that you almost never notice it. Time moves forward. Yesterday becomes today. Today becomes tomorrow. You grow older, not younger. A candle burns down, not up. Rain falls from the sky, not from the ground into the clouds. The direction feels so natural that it seems impossible to imagine otherwise. But here is the unsettling part. When physicists examine the deepest laws of nature, they discover something unexpected. Most of those laws do not seem to care which direction time moves, and that creates one of the greatest unsolved questions about reality. What actually determines the arrow of time? At first, the answer feels obvious. The future comes after the past. Case closed. But imagine watching a video of two billiard balls colliding on a table. One ball strikes the other. Energy transfers. Both move away. Now play the video backward. Surprisingly, nothing looks impossible. The reversed version still obeys the basic laws of motion. In fact, many of the fundamental equations in physics work almost identically whether time moves forward or backward. That should feel strange, because your everyday experience is filled with events that clearly have a direction. A glass falls and shatters. The pieces scatter across the floor. You never see the fragments suddenly leap together, rebuild the glass, and fly back onto the table. A drop of ink spreads through water. It never spontaneously gathers itself back into a perfect droplet. Reality seems obsessed with moving one way, yet the underlying laws often appear remarkably indifferent. So where does the direction come from? For many scientists, the leading answer involves entropy. Entropy measures the number of possible ways a system can be arranged. A highly ordered state can exist in relatively few configurations. A disordered state can exist in vastly more. As a result, systems naturally evolve toward higher entropy because higher entropy states are overwhelmingly more probable. This is why ice melts, why buildings decay, why stars eventually burn through their fuel, and why the universe seems to move from order toward disorder. The increase of entropy creates what physicists call the thermodynamic arrow of time. In simple terms, time appears to move in the direction where entropy increases. That sounds promising. But it immediately creates another mystery. Why was entropy lower in the past? Think about it carefully. If entropy is increasing today, then yesterday it was lower, and before that it was even lower. Follow the chain backward far enough, and you arrive at the early universe. For reasons nobody fully understands, the universe began in an extraordinarily low entropy state. That single fact may be responsible for the arrow of time itself, and yet it remains unexplained. Imagine finding a book lying open in the middle of a forest. You might understand the words on the pages. You might understand the plot. But if the first chapter is missing, something essential remains unknown. That is where physics finds itself. We understand how entropy creates a direction. What we do not understand is why the story started with such an unusual beginning. The deeper you explore the problem, the stranger it becomes. Because the arrow of time is not just a feature of physics. It shapes your entire existence. Consider memory. You remember the past. You do not remember the future. That feels perfectly normal. But why? Your memories are physical records stored in your brain. Creating those records involves irreversible processes that increase entropy. In other words, your ability to remember may be directly connected to the same phenomenon that gives time its direction. Without the arrow of time, memory as we know it might not exist. Neither would history. Neither would cause and effect. The very structure of experience could collapse. And then there is an even more disturbing question. Does the future already exist? Many interpretations of physics suggest that past, present, and future may all be equally real. According to this view, time does not flow at all. Instead, every moment simply exists within a larger structure called spacetime. Imagine a film reel. Every frame exists simultaneously on the reel. The characters inside the movie experience events one scene at a time, creating the illusion of motion. But from outside the film, all moments exist together. Some physicists believe reality may work similarly. If that idea is correct, then the passage of time may be partly an illusion generated by conscious experience. The future would not be coming into existence. It would already exist. You simply have not reached it yet. That possibility can feel deeply unsettling because it challenges one of the most basic aspects of human life. We experience time as movement, as change, as becoming, yet reality itself may be far stranger. Even modern cosmology raises additional questions. As the universe expands, entropy continues increasing. Stars die, galaxies evolve, energy becomes more evenly distributed. Some predictions suggest that trillions upon trillions of years from now, the universe may approach a state of maximum entropy, a state where no significant changes can occur. No usable energy remains, no new structures form, no meaningful processes unfold. Physicists sometimes call this the heat death of the universe. And if entropy truly defines the arrow of time, then what happens when entropy can no longer increase? Would time still have a direction? Would the arrow simply disappear? Nobody knows. The question remains open, and that is what makes the arrow of time such a profound mystery. We experience it every second. We build our lives around it. We measure it, organize it, fear it, and chase it. Yet when we ask why it points in one direction instead of the other, the answers begin to dissolve. Entropy explains part of the story, but not the beginning. Not the deeper reason why the universe started in exactly the state required for time to have an arrow at all. Perhaps future discoveries will reveal the answer. Perhaps the mystery reaches deeper than anything we currently understand. For now, one fact remains astonishing. Every memory you possess, every choice you make, every moment you experience depends on a cosmic direction that nobody has fully explained. Time relentlessly moves forward. The arrow is unmistakable. The reason it exists is not. Are the laws of physics permanent or evolving? There is a silent assumption hiding underneath almost everything we know about reality. The laws of physics never change. Gravity worked the same way 1 billion years ago as it does today. Light traveled according to the same rules before Earth existed. The atoms inside your body obey the same principles that governed the first stars in the universe. Science depends on this assumption. Without it, every prediction becomes uncertain. Every equation becomes temporary. Every discovery becomes a snapshot rather than a universal truth. But what if that assumption is wrong? What if the laws of physics are not permanent at all? What if they are evolving? At first, the idea sounds absurd. After all, the success of modern science comes from the remarkable consistency of nature. We launch spacecraft across billions of kilometers because physical laws behave predictably. We build technology because electrons follow the same rules every time. The universe appears reliable, almost stubbornly reliable. Yet when scientists look deeper, a strange question emerges. Why do these laws exist in the first place? Think about it. Gravity has a specific strength. Light travels at a specific speed. The fundamental forces possess precise values. The constants that govern reality seem carefully defined. But why these values? Why not slightly different ones? If gravity were a little stronger, stars might burn differently. If it were weaker, galaxies might never form. Tiny changes in some physical constants could create a universe completely unrecognizable to us, and that raises an uncomfortable possibility. Maybe the laws of physics are not inevitable. Maybe they are just the current settings of reality. Imagine waking up tomorrow and discovering that gravity had become slightly stronger overnight. The consequences would be catastrophic. Buildings would experience different stresses. Planetary orbits could shift. Biological systems would struggle to adapt. Fortunately, there is no evidence that anything like that has happened during human history. But the larger question remains, have the laws always been exactly the same? Or have they changed over cosmic timescales too vast for us to easily detect? Some physicists have seriously explored this possibility, not because they want reality to be strange, but because certain mysteries seem to invite the question. Consider the early universe. Immediately after the Big Bang, conditions were so extreme that the laws we observe today may not have existed in their current form. Many theories suggest that the fundamental forces we see now were once united into a single force. As the universe cooled, those forces separated into distinct interactions. If that picture is correct, then the laws of physics have already undergone dramatic transformations. The rules governing reality today would not be identical to those governing reality in the universe's earliest moments. That realization changes the conversation. Instead of asking whether laws can change, we begin asking whether they are still changing. And that is where things become fascinating. Scientists have searched for evidence that certain fundamental constants might slowly vary over time. Some studies have hinted at possible anomalies. Others have found no convincing evidence at all. The results remain controversial. Nothing has yet proven that the laws of physics are evolving in the present universe. But the possibility refuses to disappear completely. Because there is another mystery hiding underneath. Where did the laws come from? Most people think of laws of physics as rules imposed on reality. But what if they are not rules at all? What if they are habits? The idea sounds bizarre, yet some thinkers have suggested something similar. Imagine a universe that learns patterns over time. A universe where regularities emerge, stabilize, and become increasingly consistent. In such a picture, physical laws would not be eternal commandments. They would be the result of cosmic evolution. Much like biological evolution produced stable forms of life, reality itself could have developed stable forms of behavior. Nobody knows if this idea is correct, but it forces us to confront something we often overlook. The laws of physics are descriptions. They describe what nature does. What they do not explain is why nature follows those particular patterns. For example, we can calculate how gravity behaves with extraordinary precision. But why should gravity exist at all? Why should space and time possess exactly the properties they do? At some point, every explanation seems to hit a wall. And behind that wall sits an unanswered question. Why these laws rather than others? This mystery becomes even more intriguing when we consider the possibility of multiple universes. Some theories suggest that our universe may be one region within a much larger reality. Different regions could possess different physical constants, different particles, or even entirely different laws. In that scenario, the laws we experience would not be universal. They would be local, much like weather conditions differ from one place to another. The rules of reality could differ across a larger cosmic landscape. If that sounds unsettling, it should, because it transforms the laws of physics from eternal truths into environmental conditions. Something that feels fundamental suddenly becomes contingent. Something that feels absolute becomes temporary. And perhaps the strangest part of all is that we still do not know which picture is correct. Maybe the laws of physics are eternal and unchanging. Maybe they emerged from a deeper framework and continue evolving in ways we have not yet detected. Maybe what we call laws are simply surface patterns hiding a more profound reality underneath. The truth is that science has become extraordinarily good at describing how the universe behaves. Yet the question of why those behaviors exist remains one of the deepest mysteries ever encountered. Every star that shines, every planet that orbits, every atom that holds together depends on a set of rules that appear astonishingly precise. We trust those rules because they have never failed us. But trust and understanding are not the same thing. And until we know where the laws of physics come from, we cannot say with complete certainty whether they are permanent features of reality or chapters in a story that is still unfolding. The universe follows its laws with remarkable consistency. The mystery is whether those laws are the final foundation of reality or merely the latest version of something far deeper. Can consciousness survive beyond the brain? Few questions make people more uncomfortable than this one. Not because it is complicated, because it is personal. Every mystery about black holes, quantum physics, or the origins of the universe can feel distant. Fascinating, but distant. This question is different. It reaches directly into the center of your life, because hidden inside it is another question. What happens to you when the brain stops working? For most of human history, people have believed that consciousness survives death in some form. Different cultures imagine different destinations, different journeys, different explanations. But beneath those differences was the same intuition, the feeling that awareness is somehow more than the physical body. Then modern science arrived with a much simpler explanation. Consciousness appears to be produced by the brain. Damaged specific regions of the brain and memories can disappear. Alter brain chemistry and perception changes. Electrical activity shifts and personality can transform. Every year, neuroscience uncovers more evidence linking conscious experience to physical processes inside the skull. At first glance, the conclusion seems obvious. If consciousness depends on the brain, then when the brain dies, consciousness ends. Case closed. But strangely, the question refuses to disappear, because despite decades of research, nobody has fully explained what consciousness actually is. Think about that for a moment. Scientists can identify neural activity associated with thoughts, emotions, and decisions. They can watch different regions of the brain become active during specific experiences. But observing brain activity is not the same thing as explaining awareness itself. Imagine a scientist studying a computer. They can track electrical signals moving through circuits. They can identify which components activate during specific tasks. They can map every connection, yet none of that automatically explains why there should be an inner experience. And that is the heart of the mystery. Your brain is made of atoms. Atoms form molecules. Molecules form cells. Cells form neural networks. Somehow, from that chain of physical processes, subjective experience appears. The color red, the taste of coffee, the feeling of love, the awareness that you exist. Nobody knows exactly how that leap happens. This is sometimes called the hard problem of consciousness. Not because it is difficult to study, because it seems fundamentally different from every other problem in science. Explaining how the heart pumps blood is straightforward. Explaining how neurons exchange signals is straightforward. Explaining why any of that should produce conscious experience is another matter entirely. And that gap leaves room for a provocative possibility. What if consciousness is not entirely generated by the brain? What if the brain is doing something else? Imagine a radio. When music comes from the speaker, it is easy to assume the radio is creating the music. But the radio is actually receiving and translating signals that already exist elsewhere. Damage the radio and the music becomes distorted. Destroy the radio and the music disappears from that device. Yet the broadcast itself continues. For decades, some philosophers and researchers have wondered whether consciousness might work in a similar way. Not produced by the brain, filtered through it. The idea remains controversial and highly speculative. There is currently no accepted scientific evidence proving that consciousness exists independently of the brain. But neither has science fully explained why consciousness exists in the first place, and that keeps the debate alive. Part of the reason the question persists comes from reports surrounding near-death experiences. People who come close to death sometimes describe vivid experiences. They report sensations of leaving their bodies, encountering unusual environments, or experiencing profound clarity. Skeptics argue these events can be explained through brain activity occurring under extreme conditions. Oxygen deprivation, chemical changes, and altered neural processing may create powerful experiences that feel extraordinary. Others argue that some cases remain difficult to explain completely. The disagreement continues because the evidence remains inconclusive. What is fascinating is not that one side has won the argument. It is that the argument still exists. Because if consciousness were fully understood, the debate would largely disappear. Instead, we find ourselves facing a mystery that reaches into the foundations of reality. Some modern theories even suggest consciousness may be more fundamental than we currently assume. Just as space, time, matter, and energy appear woven into the structure of the universe, some researchers have explored whether consciousness could represent another fundamental aspect of nature. Not an accidental byproduct, not a late arrival, something present at a deeper level of reality itself. These ideas remain speculative, but they reveal how far the mystery extends. The question is no longer merely about death, it is about what consciousness actually is. And until that question is answered, certainty remains elusive. What makes this mystery so powerful is that every piece of evidence passes through consciousness itself. You can study galaxies because you are conscious. You can analyze neurons because you are conscious. You can question reality because you are conscious. Consciousness is the one thing you know more directly than anything else. And yet it remains one of the least understood phenomena in existence. Perhaps awareness is entirely produced by physical processes in the brain. If so, then consciousness may end when those processes cease. Perhaps consciousness emerges from something deeper and survives in ways we do not yet understand. If so, our current picture of reality may be radically incomplete. At present, nobody can provide a definitive answer. Not philosophers, not neuroscientists, not physicists. The mystery remains open, and that uncertainty forces us to confront a remarkable fact. You are experiencing consciousness right now. You know what it feels like to exist. You know what it feels like to think, to wonder, to remember, and to hope. Yet the source of that experience remains one of the greatest unanswered questions in reality. Whether consciousness survives beyond the brain is still unknown. What is known is something equally astonishing. The phenomenon we are trying to explain may be the most mysterious thing in the universe. Because before we can understand what happens to consciousness after the brain, we must first understand why consciousness exists at all. S. What creates the experience of selfhood? S. There is a voice in your head that feels unmistakably yours. It comments on your day. It remembers your past. It worries about the future. It tells a story about who you are and where your life is going. Most of us never question it. We wake up every morning with the same assumption. I am me. The statement feels so obvious that it seems impossible to doubt. But the moment you start looking closely, something strange begins to happen. The self you take for granted becomes surprisingly difficult to find. Think about it. Your body has changed dramatically since childhood. Almost every cell that once made up your younger self has been replaced. Your beliefs have changed. Your personality has evolved. Your memories have faded, expanded, and transformed. Yet, despite all those changes, you still feel like the same person. Why? What exactly is this thing that remains constant while everything else changes? At first, the answer seems simple. You are your body. But that explanation immediately runs into problems. If someone loses a finger, they do not become less themselves. If someone receives an organ transplant, their identity remains intact. Even dramatic physical changes leave the feeling of self largely untouched. So perhaps the self is located in the brain. That sounds more convincing. After all, your memories, emotions, and thoughts are deeply connected to neural activity. Modern neuroscience has revealed countless links between the brain and personal identity. Yet even here, the mystery refuses to disappear, because the brain is not a single thing. It is a vast network of billions of neurons exchanging signals every second. There is no obvious control center where a little version of you sits making decisions. No tiny observer watching a screen inside your head. No central commander directing operations. Scientists have searched for such a place and found nothing. Instead, the brain appears to be a collection of processes interacting with one another, which raises an unsettling possibility. What if the self is not a thing at all? What if it is a process? Imagine standing beside a river. You point at the flowing water and call it a river. Yet the water is constantly changing. The molecules passing by this second are not the same molecules that passed by a minute ago. The river appears stable, but it is actually a continuous process of change. Some researchers believe the self may work in a similar way. Not a permanent object, not a fixed entity. A dynamic process created by countless interactions inside the brain. That idea sounds abstract until you realize how much evidence supports it. Consider split-brain patients. In rare cases, surgeons have severed the connection between the brain's two hemispheres to treat severe epilepsy. What happened afterward shocked researchers. In some situations, the two halves appeared capable of acting independently, almost as though multiple centers of awareness existed within the same person. The findings challenged one of our deepest assumptions, the belief that there is a single, unified self at the center of experience. Instead, the self began looking more like a construction assembled by the brain. A story continuously being generated, and that story may be far more fragile than we realize. Think about memory. Most people imagine memories as recordings stored inside the brain, like files on a computer. But memory does not work that way. Every time you recall an event, your brain partially reconstructs it. Details change. Perspectives shift. Elements are added or removed. In other words, the story of who you are is constantly being edited, yet you rarely notice, because the brain is exceptionally good at creating the feeling of continuity. It stitches together experiences into a coherent narrative, and that narrative becomes your identity. The fascinating part is that much of this process happens automatically. You are not consciously assembling your sense of self. The brain does it for you. It gathers memories, emotions, goals, beliefs, relationships, and experiences. Then it weaves them into a single character. The character you call me. But here is where the mystery deepens. Who is experiencing that character? Imagine reading a novel. The story contains a main character with thoughts, fears, and ambitions. The character feels real because the narrative creates a sense of continuity. Now consider your own mind. There is a narrative running constantly. A story about your past. A story about your future. A story about your identity. Could the self simply be the main character in that story? Many philosophers and neuroscientists think the answer may be closer to yes than most people realize. And if they are right, the implications are profound, because it means the self may not be a permanent feature of reality. It may be an ongoing construction, a useful illusion. Not an illusion in the sense that it is fake, an illusion in the sense that it is not what it appears to be. Consider another strange fact. Much of what you do happens before you become aware of deciding to do it. Experiments have shown that measurable brain activity often begins before people consciously report making a decision. The brain appears to start preparing actions before the conscious self becomes aware of them. This finding has sparked enormous debate because it raises an uncomfortable question. If the brain initiates actions before conscious awareness arrives, then what role is the self actually playing? Are you the author of your thoughts? Or are you witnessing processes that have already begun? Nobody fully agrees on the answer, and that uncertainty reveals how mysterious selfhood really is. The more we investigate it, the less solid it appears. What feels like a single, permanent entity may actually be an evolving pattern, a process emerging from memory, perception, emotion, and consciousness. Yet despite all these challenges, the experience of self remains incredibly powerful. You feel like someone, not a collection of neurons, not a process. Someone, a center of experience moving through time, loving, fearing, hoping, remembering. The feeling is undeniable, and that is precisely what makes the mystery so fascinating. Science can describe the mechanisms associated with selfhood. Philosophy can question its assumptions. Neuroscience can identify the systems involved. But none of these fields has fully explained why the experience feels the way it does. Why there is a first-person perspective at all. Why reality is being experienced from behind your eyes rather than anyone else's. What creates the sense of being you? For now, nobody knows. The self feels like the most familiar thing in existence. Yet the moment we try to understand it, it becomes one of the most mysterious. And perhaps that is the strangest part of all. The thing you have known your entire life may still be one of reality's greatest unsolved questions. Why is reality structured rather than chaotic? Look around you for a moment. Everything appears to follow patterns. The sun rises and sets with astonishing consistency. Seasons arrive in predictable cycles. Planets orbit stars. Atoms form molecules. Molecules form cells. Cells form living organisms. Everywhere you look, reality seems organized according to rules. Now imagine the opposite. Imagine a universe where nothing followed any pattern at all. Gravity works one way today and a completely different way tomorrow. Objects randomly appear and disappear, cause and effect breakdown. Light travels at different speeds every second. Mathematics stops working without warning. Such a universe would be pure chaos. No stars could form. No planets could survive. No life could emerge. Even the simplest thought would become impossible because the brain itself depends on stable patterns. Yet somehow, reality is not like that. Reality is structured, and the deeper we investigate, the stranger that fact becomes. Because we are so accustomed to order that we rarely stop to ask why it exists. Think about a deck of cards thrown into the air. The cards scatter randomly. Disorder seems easy to create. In everyday life, chaos often appears to be the natural outcome. Buildings decay. Metal rusts. Organized systems break apart. But if chaos is so easy to produce, why does the universe contain so much structure in the first place? Why are there laws at all? Why does reality behave according to mathematical relationships instead of complete randomness? The question may sound abstract, but it strikes at the foundation of existence, because every scientific discovery rests on one crucial assumption. Nature is predictable. Scientists can perform experiments because they expect the same conditions to produce the same results. Engineers can build bridges because physical laws remain consistent. You can make plans for tomorrow because reality follows patterns rather than constantly reinventing itself. Without structure, knowledge itself would be impossible. The fact that science works at all is evidence that reality possesses deep underlying order. But that only pushes the mystery one step deeper. Where does that order come from? For centuries, many people assumed order was simply built into the universe. The laws of nature existed because they existed. No further explanation seemed necessary. Then modern physics revealed something unexpected. The deeper scientists looked, the more mathematical reality appeared. Equations describe gravity. Equations describe light. Equations describe matter, energy, and motion. Again and again, nature behaves as though it is following elegant mathematical principles. This is one of the most astonishing facts ever discovered. Mathematics is something humans develop in the realm of ideas. Yet somehow those abstract patterns describe the physical universe with extraordinary precision. Why should that be true? Why should the cosmos obey mathematical relationships at all? Some physicists have called this the unreasonable effectiveness of mathematics. Not because mathematics works. Because it works so well. The universe seems almost designed to be understood. And that creates a profound puzzle. Imagine finding a vast library hidden in the middle of a desert. Every book is perfectly organized. Every page follows logical rules. Every piece of information fits together into a coherent system. You would naturally assume some underlying principle created that order. Yet, when we look at reality itself, we often take its structure for granted. Perhaps we should not, because structured reality may be far stranger than chaotic reality. A completely random universe requires no explanation. Randomness simply happens. But a universe filled with stable laws, consistent patterns, and elegant relationships seems to demand an answer. Why this order instead of endless disorder? One possibility is that structure emerges naturally. Certain patterns may be more stable than others. Given enough time, reality could organize itself into increasingly complex arrangements. We see hints of this everywhere. Snowflakes form intricate designs. Crystals grow according to geometric principles. Galaxies organize into vast structures spanning millions of light years. Order appears capable of emerging from simple rules. But this explanation leaves an important question unanswered. Why do the rules themselves exist? Why is there a framework capable of producing order in the first place? And this is where the mystery becomes almost impossible to escape, because every explanation eventually depends on some deeper level of structure. Suppose we discover a more fundamental law explaining all other laws. Wonderful. But then we must ask why that law exists, and if we find a deeper law beneath it, the same question returns. It feels like peeling layers from an onion that never ends. Another possibility is even more unsettling. Perhaps we only observe a structured universe because structure is necessary for observers to exist. In a completely chaotic reality, conscious beings could never emerge to ask questions. There would be no stable matter, no biology, no memory, and no intelligence. Only universes possessing sufficient order could contain observers. This idea offers part of an answer, but not the whole answer. It explains why we find ourselves in an ordered reality. It does not explain why ordered realities are possible at all. And that distinction matters. Because the mystery is not merely about life, it is about existence itself. Why should reality contain laws? Why should patterns repeat? Why should cause lead to effect? Why should mathematics map onto the physical world with such incredible accuracy? The more carefully you consider these questions, the more extraordinary reality begins to appear. We often focus on the mysteries inside the universe. Black holes, dark matter, quantum mechanics. But beneath all those puzzles lies a deeper one. The fact that there is a coherent universe to investigate in the first place. A universe governed by rules. A universe capable of sustaining complexity. A universe structured enough for minds to emerge and wonder about their own existence. Perhaps future discoveries will reveal why order exists. Perhaps there is a deeper principle waiting to be uncovered. Or perhaps the ultimate reason lies beyond the limits of human understanding. For now, one fact remains undeniable. Reality could have been chaos. It could have been a meaningless storm of randomness where nothing lasted long enough to matter. Instead, it became a cosmos of patterns, laws, relationships, and structure. A reality stable enough to produce stars, planets, life, consciousness, and curiosity itself. And despite everything we have learned, we still do not know why. The universe is astonishingly ordered. The greatest mystery may be why it is ordered at all. Others do parallel versions of ourselves exist. SX, every choice you have ever made carries a ghost. The job you did not take. The message you never sent. The relationship you walked away from. The city you almost moved to. Most people have experienced that strange moment of wondering what life would look like if a single decision had gone differently. It feels like harmless imagination, but hidden inside that thought is one of the most disturbing questions in modern science. What if those other versions of your life actually exist? Not as fantasies, not as possibilities, as realities. Imagine waking up tomorrow and discovering that somewhere beyond your reach, there is another version of you. A version who made different choices. A version whose life unfolded along a completely different path. At first, it sounds like science fiction, the kind of idea that belongs in movies and novels. Yet some of the most respected interpretations of modern physics have led scientists to consider possibilities surprisingly close to this. And that is where things become deeply unsettling. Because the question is not whether alternate lives can be imagined. Everyone imagines them. The question is whether reality itself might be generating them. To understand why this idea exists at all, we need to start with something strange that happens in quantum physics. At the smallest scales of reality, particles do not always behave like ordinary objects. Instead of existing in one clear state, they can exist in multiple possible states simultaneously. At least, that is what the mathematics appears to suggest. For decades, physicists have debated what this actually means. One traditional explanation says that when a measurement occurs, all those possibilities collapse into a single outcome. One reality remains. The others disappear. Simple enough. But in the 1950s, a physicist named Hugh Everett proposed a radically different idea. What if nothing collapses? What if every possible outcome actually happens? According to this interpretation, reality branches. One outcome occurs in one branch. Another outcome occurs in another. And both continue existing. The idea became known as the many worlds interpretation. And if it is correct, its implications are staggering. Imagine flipping a coin. You see heads. In another branch of reality, another version of you sees tails. Now imagine every decision, every quantum event, every possible outcome creating additional branches. Reality would not be a single unfolding story. It would be an unimaginably vast tree of diverging histories. Within that tree could exist countless versions of you, some nearly identical, others dramatically different. There might be a version who became a musician instead of an engineer, a version who never met certain people, a version living in circumstances completely unlike your own. The concept feels almost impossible to comprehend, because we naturally think of ourselves as unique individuals following a single path through time. But this picture suggests something far stranger. The life you experience would be only one thread among countless others. And yet, before accepting the idea, it is important to understand something. There is currently no direct evidence proving that these parallel versions exist. The many worlds interpretation is one way of understanding quantum mechanics, not a confirmed fact. Many physicists find it compelling because it preserves the mathematics without requiring mysterious wave function collapses. Others remain unconvinced. The debate continues because quantum theory itself leaves room for multiple interpretations, and that uncertainty matters, because the difference between an interesting idea and a physical reality is enormous. Still, even outside quantum physics, similar possibilities emerge. Consider the size of the universe. Some cosmological models suggest that space may be infinite. If that is true, then the amount of matter available could also be effectively infinite. And if matter can only arrange itself in a finite number of ways within a given region, something remarkable follows. Patterns may eventually repeat. Given enough distance, there could be regions where matter is arranged almost exactly as it is here, perhaps even identical. That means somewhere unimaginably far away, there could exist another Earth, another history, another version of you reading these exact words, not because reality branched, simply because infinity allows repetitions. The idea sounds absurd, yet mathematically, it becomes difficult to dismiss in certain models of an infinite universe. And suddenly the question becomes much larger than quantum mechanics. It becomes a question about identity itself. What would it mean if another version of you existed? Would that person actually be you? Most people instinctively say no. After all, your consciousness is here. Your experiences are here. Your awareness is tied to this particular perspective. But then what exactly makes you you? Your memories, your personality, your body. If an identical copy existed elsewhere, sharing every memory and thought up to this moment, where would the difference begin? The question quickly becomes philosophical and deeply uncomfortable because it forces us to examine assumptions we rarely question. We like to think of ourselves as singular beings, unique centers of experience. Yet the possibility of parallel selves challenges that certainty. It suggests identity may be more complicated than it appears. Perhaps the most fascinating part is not whether these alternate versions exist. It is what their possibility reveals about reality. A universe capable of generating parallel selves would be far stranger than our everyday intuition suggests. It would mean that existence is not a single story unfolding along one path. It would mean reality contains layers of possibility far beyond anything we directly observe. For now, no experiment has definitively confirmed the existence of parallel versions of ourselves. No telescope has detected them. No laboratory has measured them. The idea remains one of the most provocative possibilities in modern science. And yet it refuses to go away. Because every attempt to understand the deepest layers of reality seems to open doors to worlds more bizarre than the last. Perhaps there are countless versions of you living countless different lives. Perhaps there is only one. At present, nobody knows. But somewhere between quantum theory, cosmology, and philosophy lies a question that remains unanswered. When you wonder about the life you could have lived, are you imagining an impossible fantasy? Or are you catching a glimpse of realities that might actually exist? Is objective reality ultimately knowable? Imagine that everything you have ever experienced is happening behind a window. You can see through it. You can learn from it. You can study what lies beyond it. But no matter what you do, you can never step outside and look at reality directly. That sounds like a strange thought experiment, yet it may describe the human condition more accurately than most people realize. because every fact you know about the universe has reached you through a filter. Light enters your eyes, sound enters your ears, signals travel through nerves. Your brain processes those signals and constructs an experience that feels immediate and real. You never encounter reality directly. You encounter your experience of reality. And that simple observation leads to one of the deepest questions ever asked. Can we ever truly know objective reality? At first, the answer seems obvious. Of course we can. Science has mapped galaxies, decoded DNA, uncovered the structure of atoms, and revealed the age of the universe. Human knowledge has expanded so dramatically that it can feel as though reality is gradually surrendering all its secrets. But the deeper we look, the more complicated the situation becomes. Take color, for example. Most people assume colors exist exactly as they appear. A red apple looks red because redness is a property of the apple. Simple. Except that is not what science tells us. The apple reflects certain wavelengths of light. Your eyes detect those wavelengths. Your brain translates them into the experience you call red. The redness itself exists inside conscious experience, not out in the world the way it feels. The same applies to sound. Outside your mind, there are only pressure waves moving through air. The sensation of sound emerges when your brain interprets those vibrations. Even something as basic as the passage of time may be influenced by how consciousness processes information. Again and again, reality appears less direct than it first seems. The world you experience is not reality raw and untouched. It is reality filtered through perception. And that creates a profound challenge. If every observation passes through a perceptual system, how can we ever know what reality is actually like independent of that system? Imagine wearing a pair of glasses from birth. You have never removed them. You have never seen the world without them. Over time, the lenses become invisible because they are all you have ever known. Now imagine trying to determine what the world looks like without the glasses. How would you do it? Every attempt would still be made through the lenses. Many philosophers argue that humanity faces a similar problem. We investigate reality using minds that are themselves part of reality. We cannot step outside our own perspective. We cannot compare our experience to some completely unfiltered version of existence. And yet science has achieved extraordinary success despite this limitation. That fact is important because it suggests our perceptions are not entirely detached from reality. If they were, airplanes would not fly, computers would not function, spacecraft would not reach distant planets. The remarkable predictive power of science implies that our models capture something genuine about the structure of the universe. But capturing something is not the same as capturing everything. Think about a map. A good map can be incredibly useful. It can guide travelers across entire continents. It can reveal relationships that would otherwise be difficult to see. Yet no map is the territory itself. Every map simplifies. Every map leaves details out. Every map represents reality rather than becoming reality. Some scientists believe our theories may work in much the same way. They may be increasingly accurate maps of the universe without ever becoming the universe itself. This possibility becomes especially intriguing in modern physics. Quantum mechanics, one of the most successful scientific theories ever developed, predicts experimental results with astonishing precision. Yet physicists still disagree about what the theory actually says about reality. Different interpretations produce the same predictions while describing fundamentally different pictures of what exists. That should make you pause. because it suggests that predicting reality and understanding reality may not be the same thing. We may know how reality behaves while remaining uncertain about what it truly is. And then there is consciousness, the one thing through which all knowledge passes. Every scientific observation ultimately appears within conscious experience. Every equation is understood through consciousness. Every experiment is interpreted through consciousness. Yet consciousness itself remains deeply mysterious. We still do not fully understand why subjective experience exists at all. This creates a strange loop. The tool we use to understand reality is itself one of reality's greatest mysteries, which raises another possibility. Perhaps some aspects of objective reality lie permanently beyond human understanding. Not because they are hidden, because our minds may not be equipped to grasp them. Consider a dog trying to understand calculus. No amount of effort will bridge the gap because the necessary cognitive machinery simply is not there. Now ask yourself a more unsettling question. Could humans face similar limitations? Could there be truths about reality that exceed the capacities of the human mind? Truths as inaccessible to us as advanced mathematics is to a dog. The possibility is difficult to dismiss. After all, our brains evolved to help small groups of primates survive on a particular planet. They were not designed to comprehend the ultimate structure of existence. And yet, despite all these limitations, something remarkable remains true. We keep learning. We keep discovering. We keep pushing the boundaries of understanding further than previous generations thought possible. Every century reveals aspects of reality that once seemed forever beyond reach. That fact offers reason for optimism. Perhaps objective reality is ultimately knowable. Perhaps every mystery will eventually yield to deeper investigation. Or perhaps knowledge will always approach reality without fully reaching it, like a traveler moving toward a horizon that recedes with every step. For now, nobody knows. The question remains open. But what makes it so fascinating is that it sits underneath every other question humanity has ever asked. Before we can understand the universe, consciousness, time, or existence itself, we must confront a deeper uncertainty. Whether the reality we seek is something we can fully know at all. And until that question is answered, every discovery carries a hidden mystery. Not just what reality is, but whether we are seeing reality itself, or only the most detailed map we have managed to draw. Thus, could reality be based on computation rather than matter? For most of human history, people assumed reality was made of stuff, solid things. Rocks, oceans, mountains, planets, stars, and eventually atoms. As science advanced, we kept breaking matter into smaller pieces, convinced that somewhere at the bottom we would find the ultimate building blocks of existence. And for a long time, that seemed exactly where the story was headed. But then something unexpected happened. The deeper scientists looked, the less reality resembled the solid world we experience every day. Atoms turned out to be mostly empty space. Particles behaved like probabilities. Matter began looking less like tiny objects and more like mathematical relationships. And gradually, a strange possibility emerged. What if matter is not the deepest layer of reality? What if something else comes first? Imagine opening your favorite video game. You see mountains, cities, rivers, weather systems, and characters moving through a seemingly physical world. To the characters inside that world, everything appears solid and real. But beneath the graphics lies something entirely different. Code information. Computation. The visible world emerges from an invisible process running underneath. Now consider a question that sounds almost ridiculous. What if our universe works in a similar way, not necessarily as a literal video game created by programmers, but as a reality whose deepest foundation is computation rather than matter? At first, the idea feels absurd. After all, matter seems obviously real. You can touch a table, you can hold a stone, you can feel the ground beneath your feet. Computation sounds abstract by comparison, yet modern science has repeatedly revealed that common sense is not always a reliable guide to reality. And surprisingly, several discoveries have made the computational view harder to ignore. Think about what happens inside a computer. At the lowest level, everything reduces to information being processed according to rules. Images, music, text, and entire virtual worlds can emerge from simple operations performed billions of times per second. Complexity arises from underlying patterns. The same principle appears throughout nature. DNA stores information, cells process information, brains process information. Entire ecosystems depend on the flow and transformation of information. Everywhere scientists look, information seems to play a fundamental role. This has led some researchers to ask a provocative question. What if information is more basic than matter itself? The physicist John Wheeler famously summarized this idea with a phrase that became highly influential: "It from bit." The suggestion was simple but profound. Physical reality may ultimately emerge from informational processes. In other words, things arise from information, not the other way around. That possibility becomes even more intriguing when we examine the laws of physics. Reality behaves with extraordinary mathematical precision. The universe follows rules so consistent that equations can predict the behavior of distant galaxies, subatomic particles, and everything in between. Why? Why should reality obey mathematical rules at all? A computational universe offers one possible answer. Computation requires rules. Every calculation follows a defined structure. If reality is fundamentally computational, then mathematical order would not be surprising. It would be unavoidable. The universe would behave mathematically because mathematics would be woven into its foundation. And then quantum physics enters the story. At the quantum level, reality often appears less like a collection of physical objects and more like a system of information. Particles can exist in multiple possibilities. Quantum states contain information about potential outcomes. Measurement seems deeply connected to how information becomes defined. Some physicists have argued that information may be one of the most fundamental ingredients in nature. Not matter, not energy. Information. That idea sounds strange until you realize how often matter itself appears secondary. Consider a book. The paper is not what makes the book meaningful. The ink is not what makes it meaningful. The meaning comes from the information encoded in the arrangement. Change the arrangement, and you change the story. The physical material can remain almost identical, while the informational content becomes completely different. The same principle appears throughout reality. Patterns often matter more than the substance carrying them. And that observation has led some thinkers to wonder whether the universe itself is ultimately a pattern being processed. Of course, this raises an obvious question. If reality is based on computation, what is doing the computing? The answer is that nobody knows. Some theories suggest computation could be an intrinsic property of reality itself. No external computer would be required. The universe would effectively compute its own evolution. Others speculate about deeper levels of existence beyond our observable cosmos. But these ideas remain highly speculative. At present, there is no definitive evidence proving that reality is computational at its core. The concept remains a possibility rather than a confirmed fact. Yet it continues attracting serious attention because it addresses mysteries that conventional views struggle to explain. Why is the universe so mathematical? Why is information so fundamental? Why do simple rules generate such extraordinary complexity? Why does reality often resemble a system processing possibilities rather than a collection of solid objects? The computational perspective offers one framework for thinking about these questions. Whether it is correct remains unknown. Perhaps matter truly is the foundation of existence. Perhaps information comes first. Perhaps both emerge from something even deeper that we have not yet discovered. What makes the idea so fascinating is not that it provides final answers. It is that it completely changes the way we think about reality. Instead of imagining a universe built from things, we begin imagining a universe built from processes. Instead of objects, patterns. Instead of substance, information. And suddenly, the world around us starts looking very different. The stars, the planets, your thoughts, your memories, and even your sense of self become part of an immense informational structure unfolding across cosmic scales. Whether that picture is true remains one of the great unanswered questions. But if reality is ultimately based on computation rather than matter, then everything we call physical may be the visible surface of a much deeper process, a process that has been running since the beginning of the universe, and perhaps long before that. As what lies beyond the observable universe? A sex, there is a boundary surrounding everything you have ever seen, studied, or imagined, not a physical wall, not a barrier floating in space, a horizon, a limit beyond which we cannot see. Right now, as you listen to this, light is traveling toward us from distant parts of the cosmos. Some of that light has been crossing space for billions of years. It carries information about galaxies, stars, and events that occurred long before Earth even existed. But there is a catch. The universe is not infinitely old. Because light travels at a finite speed, there is only a certain distance from which light has had enough time to reach us since the beginning of cosmic expansion. Everything beyond that distance remains hidden. Not because it does not exist, because its light has not arrived. This hidden boundary is what scientists call the observable universe, and it contains an almost unimaginable amount of space. Hundreds of billions of galaxies, trillions upon trillions of stars, vast structures stretching across cosmic distances, so enormous that the human mind struggles to picture them. Yet, despite its incomprehensible size, the observable universe may be only a tiny fraction of reality. And that is where the mystery begins. Because once you understand what the observable universe actually means, a simple question becomes unavoidable. What lies beyond it? At first, the answer seems obvious: more universe. After all, there is no reason to think reality suddenly stops at the edge of what we can observe. The boundary exists because of our limitations, not because of a known physical ending. Imagine standing on a beach and looking toward the horizon. The ocean appears to end where the sky meets the water. But you know better. The horizon is not an edge in reality. It is merely the limit of what you can currently see. Many cosmologists suspect the observable universe works in much the same way. The cosmic horizon may simply mark the limits of observation, while reality continues far beyond. If that is true, then regions of space exist that we will never directly observe. Not because technology is inadequate, because the expansion of the universe prevents their light from ever reaching us. No matter how advanced future civilizations become, some portions of reality may remain permanently inaccessible. That idea alone is astonishing. Entire galaxies could exist forever beyond humanity's reach. Whole cosmic histories unfolding where no information can ever cross the distance separating us. But the mystery deepens further, because once we move beyond the observable universe, certainty begins to disappear. Scientists can make educated inferences based on the evidence available. Yet direct observation becomes impossible. And where observation ends, possibilities multiply. One possibility is that space simply continues indefinitely. Beyond our observable region lie more galaxies. Beyond those galaxies lie more galaxies still. The pattern repeats endlessly. If this picture is correct, then the universe may be vastly larger than we currently imagine, perhaps even infinite. In such a reality, the observable universe would be like a single drop in an endless cosmic ocean. But there is another possibility. The universe could be finite while remaining unimaginably large. Just as Earth's surface has no edge despite containing a finite area, space itself might possess a shape that curves back on itself. Travel far enough in one direction, and you might eventually return to where you started. In that case, the regions beyond our observable horizon would still exist, but they would form part of a larger finite structure. And then the possibilities become even stranger. Some theories in modern cosmology suggest that what we call the universe may not be the whole story. Our observable region could be one small pocket within a much larger reality, a reality containing countless other cosmic regions, separated by distances so vast that communication becomes impossible. This idea appears in several versions of what is commonly called the multiverse. According to some models, different regions could possess different physical conditions, different constants, different histories, perhaps even different laws of physics. If that sounds unbelievable, remember that these ideas emerge not from science fiction, but from attempts to understand the mathematics of cosmology and fundamental physics. The challenge is that evidence becomes extraordinarily difficult to obtain. When something exists beyond the observable universe, observing it directly becomes impossible by definition, and that leaves scientists in a difficult position. They can develop theories. They can test indirect predictions, but complete confirmation may remain forever out of reach. The mystery becomes philosophical as well as scientific, because it forces us to confront the limits of knowledge itself. For most of human history, people assumed reality ended not far beyond what they could see. Ancient civilizations believed the world was relatively small. Then exploration expanded the map. Earth became larger. Then the solar system became larger. Then the galaxy became larger. Then the universe became larger. Again and again, every apparent boundary turned out to be another horizon, another limit waiting to be crossed. That pattern makes many scientists cautious about assuming our current horizon represents anything fundamental. History suggests reality is often bigger than expected, much bigger. And perhaps the most humbling possibility is that whatever lies beyond the observable universe may completely transform our understanding of existence. There could be structures larger than anything we currently know, regions operating under conditions unlike anything found here, levels of reality that make our observable cosmos seem small by comparison, or perhaps beyond the horizon lies more of the same. An endless continuation of galaxies and stars stretching beyond comprehension. At present, nobody knows. The observable universe defines the limits of what we can currently access, not necessarily the limits of what exists. And that distinction matters, because it means the greatest part of reality may lie beyond our view, beyond our telescopes, beyond our measurements, beyond anything we can directly observe. Every night, when you look up at the stars, you are seeing only a tiny portion of what may be out there, a visible island surrounded by an ocean of unknowns. And somewhere beyond that cosmic horizon, beyond every galaxy we can detect and every signal we can receive, reality continues. The question is not whether something lies beyond the observable universe. The question is how much, and the honest answer is that we still have no idea. Are cause and effect fundamental or emergent? Effects every moment of your life is built upon a simple assumption. Things happen for reasons. You press a switch and a light turns on. You drop a glass and it falls. You study hard and your knowledge grows. Every event appears connected to another event that came before it. Cause leads to effect. The principle feels so obvious that it seems impossible to imagine reality without it. In fact, cause and effect are so deeply woven into human thinking that we use them to understand almost everything. Science depends on them. Logic depends on them. Everyday decision-making depends on them. Without cause and effect, the world would seem completely unpredictable. And yet, when physicists began exploring the deepest layers of reality, something strange happened. The certainty started to crack, because the closer we get to the foundations of existence, the less obvious it becomes that cause and effect are fundamental features of the universe. At first, this sounds absurd. How could cause and effect not be fundamental? After all, every experience seems to confirm their existence. But imagine watching a movie. On the screen, one scene causes the next. A character makes a choice. Consequences follow. Events unfold in a logical sequence. From inside the story, cause and effect appear absolutely real. Yet underneath the movie lies something different. A collection of individual frames. The narrative emerges when the frames are arranged in a particular order. The story feels fundamental, but it may actually be emerging from something deeper. Some physicists wonder whether cause and effect might work in a similar way, not as the foundation of reality, but as a pattern that emerges from more basic processes. This possibility becomes especially interesting when we examine quantum mechanics. At the quantum level, particles often behave in ways that challenge ordinary intuition. Events sometimes appear probabilistic rather than strictly determined. Instead of one guaranteed outcome, reality presents a range of possibilities. Only probabilities can be predicted with certainty. This creates an uncomfortable question. If fundamental events are governed by probabilities, where exactly does traditional cause and effect fit in? Imagine rolling a die. You can explain why the die moves. You can calculate the forces involved. But predicting the exact result becomes much harder. Quantum mechanics takes this uncertainty even deeper. Certain outcomes appear inherently unpredictable, not because information is missing, because nature itself seems to operate probabilistically. For some people, this suggests that causality breaks down at the smallest scales. Others disagree. They argue that deeper causes may still exist, hidden beneath our current understanding. The debate remains unresolved. And then things become even stranger. Some experiments have produced situations where the order of events becomes surprisingly ambiguous. In everyday life, causes always come before effects. That seems non-negotiable. A match must be struck before a flame appears. A stone must be thrown before a window breaks. Yet certain interpretations of quantum theory allow scenarios where the sequence of events becomes less clear than our common sense expects. Reality begins behaving in ways that blur the neat distinction between before and after. The implications are profound, because if causality depends on the structure of time, and time itself emerges from something deeper, then perhaps cause and effect emerge as well. Suddenly, what seemed like the most basic feature of existence starts looking like a higher-level phenomenon, a product rather than a foundation. To understand why this possibility matters, think about temperature. Most people treat temperature as a fundamental property: hot, cold, warm, simple. But temperature is actually an emergent phenomenon. Individual molecules do not possess temperature in the way we experience it. Temperature emerges from the collective motion of vast numbers of particles. It is real, extremely real. Yet it arises from deeper processes. Cause and effect may be similar. The orderly chain of events we observe could emerge from underlying dynamics that do not contain causality in the familiar sense. And if that sounds unsettling, it should, because cause and effect are not merely scientific concepts. They shape how we understand ourselves. Think about every decision you have ever made. You believe your choices lead to consequences. You believe actions create outcomes. Your entire sense of responsibility depends on causal relationships. If causality is emergent rather than fundamental, then one of the most important features of human experience may be a higher-level pattern rather than a basic law of reality. That does not mean cause and effect are illusions. Emergent phenomena are still real. Money is real even though it emerges from social agreements. Traffic jams are real even though no single car creates them. Consciousness may be real even if it emerges from neural activity. Emergence does not imply unreality. It simply means that something arises from deeper interactions. And that brings us to one of the biggest mysteries in modern physics. Many attempts to unify quantum mechanics and gravity suggest that spacetime itself may not be fundamental. Space and time could emerge from more basic structures. If that turns out to be true, then causality may emerge alongside them. The entire framework through which we understand events could be a product of deeper processes hidden beneath reality's surface. Nobody knows for certain. Some physicists believe causality is fundamental and irreducible. Others suspect it emerges from underlying informational or quantum structures. Both possibilities remain alive, and each carries extraordinary implications. If cause and effect are fundamental, then reality rests upon a deep framework of ordered relationships stretching all the way down. If they are emergent, then the universe is even stranger than it appears, with one of its most familiar features arising from hidden layers beneath our perception. For now, the mystery remains unsolved. Every scientific theory relies on causality to some degree. Every human life is built around it. Yet when we ask where cause and effect come from, the answers begin to dissolve. We know that causes and effects shape the world we experience. What we do not know is whether they belong to the deepest level of reality, or whether they emerge from something even more fundamental. And if the second possibility is true, then one of the most basic assumptions we make every day may be only the visible surface of a much deeper mystery. Ross, will we ever reach the ultimate explanation of reality? Say every generation believes it is getting closer. Closer to the final answer. Closer to the moment when humanity will pull back the last curtain and finally understand what reality is. And to be fair, there are good reasons to think that way. A few hundred years ago, people did not know what stars were. They did not know what causes disease. They did not know that atoms exist, that galaxies fill the cosmos, or that space and time are connected in ways that defy common sense. Then discovery after discovery transformed our understanding of the universe. Mysteries that once seemed impossible became textbook knowledge. The progress has been so extraordinary that it naturally leads to an exciting question. If we keep learning at this pace, will we eventually reach the ultimate explanation of reality? Will there come a day when every question is answered? A day when the deepest secrets of existence are finally understood? At first, the idea feels reasonable. After all, science has a remarkable track record. Again and again, problems that appeared unsolvable eventually yielded to human curiosity and persistence. Lightning was once mysterious. Now we understand electricity. The motion of planets once seemed magical. Now we can predict their positions centuries into the future. The world has repeatedly become more understandable. So why should reality have a final mystery that remains forever beyond reach? But the deeper you think about it, the more complicated the question becomes. Because every answer humanity discovers seems to generate new questions. Consider atoms. For a time, atoms were believed to be the fundamental building blocks of existence. The word itself means indivisible. It sounded like the end of the search. Then scientists discovered that atoms contain smaller components: protons, neutrons, and electrons. Problem solved. Until those particles turned out to contain deeper layers of mystery as well. The pattern keeps repeating. Every apparent endpoint becomes a doorway. Every final answer becomes the beginning of another investigation. It is almost as though reality continuously retreats just beyond the edge of our understanding. Imagine climbing a mountain because you want to see the entire landscape. You reach the summit and discover another mountain beyond it. You climb that one and find another, and another. The view expands with every ascent, but the horizon never disappears. Knowledge often feels exactly like that. The more we understand, the more we become aware of what we do not understand. And nowhere is this clearer than in modern physics. Scientists possess theories capable of predicting experimental outcomes with astonishing precision. Yet some of the most important pieces of the puzzle remain missing. We do not fully understand consciousness. We do not know what dark matter is. We do not know what dark energy is. We do not know why the laws of physics possess their particular form. We do not know why the universe began in the way it did. And perhaps most importantly, we do not know whether there is a final level beneath which no further explanation exists. That last question is crucial, because an ultimate explanation would require something extraordinary. It would need to explain everything without requiring another explanation behind it. A true foundation, a stopping point, something that exists necessarily rather than contingently. But is such a thing even possible? Suppose tomorrow scientists discover a single elegant equation capable of describing every force, every particle, and every interaction in the universe. Many people would celebrate it as the final theory, the ultimate explanation. Yet almost immediately, another question would arise. Why that equation? Why those principles? Why does reality obey those rules instead of different ones? The mystery would not disappear. It would simply move one level deeper. This is what makes the search so fascinating. Every explanation seems to stand upon assumptions that invite further questions. No matter how deep we go, curiosity keeps finding another door to open. Some philosophers believe this process never ends. According to this view, reality may be fundamentally inexhaustible. There may always be deeper layers waiting beneath whatever explanation we currently possess. Others disagree. They believe a final theory is possible, a framework so complete and fundamental that no further explanation would be required, a genuine endpoint to the search. At present, nobody knows which possibility is correct, and there is another complication. Even if an ultimate explanation exists, can the human mind fully understand it? This question is often overlooked. We tend to assume that if something is real, it must eventually become understandable. But nature does not owe us that privilege. Human intelligence evolved to solve survival problems on a particular planet. We became good at recognizing patterns, predicting outcomes, and navigating our environment. That does not guarantee we are equipped to comprehend the deepest structure of existence. There may be truths that exceed our cognitive limits, concepts so far beyond human intuition that understanding them completely becomes impossible. Just as a fish cannot grasp astrophysics, humanity may face boundaries imposed by the architecture of the mind itself. And yet, despite all these obstacles, something remarkable continues to happen. We keep making progress. Questions that once seemed unreachable become approachable. Ideas that once sounded impossible become measurable. Reality reveals more of itself than anyone expected. That fact makes it difficult to be pessimistic. Humanity has repeatedly shattered assumptions about what can be known. Perhaps future generations will uncover principles that make today's mysteries seem simple. Perhaps they will move closer to an ultimate explanation than we can currently imagine. Or perhaps every answer will continue generating deeper questions forever. For now, the truth remains uncertain. We do not know whether reality possesses a final explanation. We do not know whether the search has an endpoint. We do not know whether ultimate understanding is possible. But maybe that uncertainty is part of what makes the journey so extraordinary, because the history of human knowledge is not the story of certainty. It is the story of curiosity refusing to stop. A species looking into the darkness and asking one more question, then another, and perhaps the greatest mystery is not whether we will ever reach the ultimate explanation of reality. Perhaps the greatest mystery is whether reality itself has an ultimate explanation waiting to be found. Until we know the answer, the search continues, and every discovery brings us face to face with the same beautiful possibility. That beyond everything we currently understand, there may still be something even deeper waiting to be revealed.